Okay, so through the crudest of interfaces, which is simply a string of numbers here, corresponding to the hip pitch, hip yaw, hip roll, knee and ankle, I can get this leg to move. So for example, that raises the leg to the side. That returns it. Up. Down. Hip yaw. Hip pitch. Is that. So let's see if we now also bend the knee. Oh no, that's not the knee, that's the roll. Quite nice though. So this is the knee. Okay, so raise at the hip pitch, and we're going to bend the knee more. More than that. What do I flicked? It's quite strange to see. Okay, and now let's roll it out a bit more. Just this, I think. Yes. And let's pull it back. Okay, so if I try and play that quickly in sequence. That's quite interesting. So the hitting hard is requires, well, ultimately requires skill, but at this point it seems to require luck, and that's because I managed to build up some momentum. But I'm not very good at this kind of stuff, so you'll have to bear with me. And then a long way back, because it's just scrolling through the commands. Back down we go. This is the hip pitch mechanism of the HOPEJr, which will take the hand, with the software being developed by Hugging Face, and give it a pair of legs. To make it as cheap as possible, I'm using these, which is a quasi-direct drive, which is just a fancy way of saying that it has a very low reduction gearbox. So you can get motors like hoverboards, which have no gears at all. They're very high torque, but they're very, very heavy because they have a lot of copper. And a kind of compromise, which seems to work out really well, is to use an outrunner style brushless motor with a low reduction gearbox, in this case 7.5 to 1. And this is, in truth, not fully tested by me yet, but looks really good on paper. And it's got an excellent price to performance ratio. In China, you can get these for $65. In Europe, they cost me about 110, 105 euro. And in the US, I don't know actually. But for the torque you get out of it, it's about twice as cost effective as any of the others, if not more. There's a range. You can get stuff on Ali, but it generally won't have gearboxes. You can go direct to humanoid manufacturers. But these bad boys, these are very, very tasty. I think. I've not built a whole robot. I've not built a whole robot with one yet. So, got to find out. Anyway, I have incorporated the guts of the series elastic actuator mechanism from the Hope, from the big one. And that also seems to work pretty well. Much simpler. Got rid of many parts. And everything is done in oversize 3D prints, because that takes advantage of a lovely property of 3D prints, which is that most of the material is at the extremities. So it makes it very efficient for weight. The final versions, I suspect, are going to be printed entirely in carbon fibre reinforced nylon, because it's just so much stronger. But I have been enormously impressed with how much PLA has improved since I last looked at it. And I felt confident to prototype in colourful PLAs. And when it breaks, which I'm sure it will, wouldn't it be good if it didn't? But when it breaks, it will tell me where the weak points are. I suspect obvious ones are the fat and miss up a bit. But we'll see. But I won't try to break it straight away. I'm going to try and make it hop up and down a bit. We shall see how we get on. Anyway, very excitingly, I'm about to assemble the hip yaw. This has a configuration which is becoming known as FAR, which means you have pitch, and then you have what would be abduction. I'll show you the bit like this. This is not quite the right bit, but give you an idea. Abduction, flexion, and then rotation, which is similar to how the arm setup is done. So I've just kind of naturally done that. Apparently that is the best way of doing it. We shall see. First guess. Some neat tricks. This ring splits off, it splits apart. Lots of bearings in there. 500mm belt, MT5, just the normal one. It's quite a bit cheaper. 10mm wide. Lots of bearings, lots of screws, but other than that, really quite simple. So, to assemble the yaw joint, you are going to need a motor, .24 volts, almost 300 RPM, and 12 Newton meters, 120 kilogram centimeters. That's not enormous. It is in fact 1/10 what the Unitree G1 generates at the hip, and that's a bit of a problem. So the solution to that is to add belts, which is what I've done here. This is a 4:1 ratio. And belts are acceptable because when they're set up well, timing belts are actually very precise. They can transmit plenty of power as well. They're now used maybe exclusively, but they're certainly used in a lot of Harley Davidson motorbikes, so there's no problems with power transmission if you get the spec right. And the transparency is still very low because of the moving inertia and the friction are very low. Nonetheless, it does up the reduction of the quasi-direct drive to kind of borderline what you can be calling a quasi-direct drive. So that's a little bit of an experiment, and we shall see how much the series elastic puts back into the dynamics and at what cost of the control. This will be the trade-off, of course, but by putting physical spring elements in, you can improve the mechanical characteristics, but the control is well, certainly harder in the sense that you can't solve it with classical control. But you know, these days, let's just chuck loads of data and loads of modelling and loads of really clever stuff, which I only have a very vague inkling about, but that's fine, because there's loads of super talented, super clever people that are dying to work on the software, and those that are already doing so are making enormous progress. So just gonna put it out there, see what people do with it. Low cost, fairly full spec, child size, semi-dexterous, which means it can move the fingers to anywhere in space, but it can't change the pressure direction or the direction of pressure which is being applied in a way that you can kind of hook back onto objects. You can pick up a basketball, which clearly you're not getting your fingers all the way around it. You won't be able to do that, but it'll have some dexterity. Let me see how far we can get with it. Bill of materials, not including the computer, and arguably not including very high-spec batteries, but I reckon you can do it for about $2,500, not including the 3D printer, but possibly including the filament. Yeah, 2.5, 3 grand, that kind of region. That I think would be quite interesting for people. Anyway, I digress. The setup is, in my nomenclature, in my naming system, pitch, which is a belt down to here, yaw, which is the leg moving away from the side of the body, and roll, which is rotation down the long axis on the femur. And this is becoming known as FAR for flexion, abduction, and roll. But it's just a nice, efficient way of doing it. The yaw, therefore, is going to pass perpendicular to the direction of pitch. Well, I have a feeling that introducing very slight offsets is actually quite crucial to producing a particular kind of gate. But this is kind of like the vanilla, the starter. Everything is set up dead square. So we'll see how far we can get with control. But it seems to me that passive dynamics are going to come in at some point to play. We shall see. The mechanism, oh, let me go and grab one. The mechanism is like this, and I didn't use a different cut of plaster on that, didn't use a different kind of plastic on that one, but up in the hip you can see, hopefully, that is like that. The orange bit is that green bit. And the output is via that spring. That's what creates the mechanism. This has got more down here, these are moved around. And if I've done my design correctly, it can be kind of assembled on the outside and then slotted into a large bearing, which goes here. So the way that mechanism goes together is with M4x60. And a bunch of bearings. Okay, so that was probably from the last time I connected the inserts, or the last time I heat inserted the inserts, because that will make it go tight. Crikey, it's gone tight. So I didn't go quite as deep as I should have done. Just going to press that one in a bit deeper. Well, not beautiful, but below the surface, which is what matters. This will take the top of the rotation motor. Huh, which I see has gone slightly wrong. How did that happen? Huh. Okay, there should be holes here and here. Oh yes, that's right, it gets moved around for access. Okay, yes, I remember. Huh, very good. Yes, this one gets undone and then goes to that point. So you can screw nicely through from the top. Okay, very good, minor detail. For the Yorvo, it's fine. This motor hangs out the back. I have I'm almost certain I'm going to have to upgrade this one to a belt as well. But for now, on this build, I'm just going to put it through as a direct drive assembly. Which you can see up here. This is how this is all connected together. For the knee and the ankle, the motor is actually offset and the belt is increasing the torque onto this mechanism. And I think that means that it will act as a higher density dynamic storage or energy storage, but the hip will have better accuracy and higher stiffness. So it's just something which is being enforced by the aspect ratio of the design. Hopefully it works out to be a good thing. If not, I'll have to add another belt stage or something else, but cross that bridge and when we come to it. For the yaw, the way that this goes together is you need a 6809 bearing, and then these pieces clip in. It's worth, before you assemble for the first time, checking that they're clear. You don't have any debris trapped in there. Here you can see sometimes you get a little error in print. If need be, apply a little bit of heat from a flame torch lighter is what I use. Hopefully that just all clips in. These will clip either side like that, and then the key goes in the bottom and secures it there. The motor, there are holes all the way around, but generally for ease I'm locating the peg up into here. And it should be a pretty tight fit, but then it should pop down. Might pop up when you let go. That's good. It's toleranced, I think, probably smack on size, so either a bit of give in the plastic or a tiny bit of shrinkage during printing, and you should have just enough clearance, or when you force it, it'll just pop on. And then we're going to use some short countersunk screws to hold that in place. And they are not out at the moment. Generally, the rule is to just do things up enough to get position, and once you're happy, you can do them all up tight. And the key, really, you only need one just to stop it falling out. Just press down, time those up. Much of this is going on slightly below full strength, and the reason for that is that I do kind of want to see where it breaks. But that will attach a bearing very concentrically to the powered output shaft of the motor, and that bearing fits in here into this cavity I'm going to place a spring, and the spring has a large ground surface, and you want that to be there, because that is what is going to press on the bearings, which are held by the torque carrier. That one needs to be assembled first, and then you'll drop it into place with another bearing on here. One clamp there, one clamp there. Okay. So this is attached to the motor. First thing we're going to have to do, of course, is we're going to turn the motor on, and we're going to set a 0 position. So the up is where we think it is. Okay, so where is it? Doesn't like it. Gonna run anyway. Don't know why it doesn't like it. It's for HOPEJr debugger, and all that really seems to matter is that you use, I'm trying to find the packet for that, a CAN adapter which has a particular kind of chip built in. That's a CH3040. If you don't have a CH3040, it won't work. If you do have one, it will work pretty easily. And then, once everything's connected up, follow a wiring diagram for that, but you've got 2 CAN lines and a ground, you connect them up to the correct connections on the USB plug-in. Connect 24 volts to the power, black is always ground, red is always positive. Plug it in, nothing happens. You apply power, nothing happens, but on your ammeter, you will see some power being drawn. Here's connections, I'm sure it's even labelled. Ground, and then the 2 CAN lines, can't remember which is which. As you power it up, you will see messages appear. Put in position mode, turn it on, don't forget to give it some velocity. Oh yes, then press continuously. When you change the position, and press start, it will move. And we can now assemble this. These are quite a tight fit, so depending on how well set up your printer is, you might have to drill these out. That's handy if you have a long drill. And just drill them out. One thing I would say with plastic is that it's not just a question of spinning the drill. Unless you get a very long reamer, which would be the best tool for this. It's also a good idea to pass the drill up and down a bit. The advantage with a long drill, you have to be less accurate with your angles when you're first drilling. And just be careful to get rid of the swarf. This kind of twist drill will leave a slight spiral in the hole, which will then be unable to cut itself, and the moving backwards and forwards reduces that significantly. Drill them all. For now I'm only going to drill the 2, I'm only going to screw the 2 long ones, and maybe one of these back here just for positioning. Yeah, so Again, it's not making everything max strength. See what breaks, it'll be the 2 bolts. And this design there, 75. I will make them slightly different in subsequent designs, because 75 is not a common size. And when they screw down, they will pull in tight to the motor here. And here it's going to be a short one. In 4x10 or 12. It's not 4x12. See if that goes all the way down. Yes, I expect it will. And 4x12 is the size you want. Do it tight now. And they should end up flush to that surface. As you can see, firmly attached to the output of that motor. Normally, of course, you would drill straight over the bin, but I'm going to put the camera over the bin. Okay, so output shaft is attached. Make sure this is clear of any swarf. Might also be worth putting a little bit of heat into these before you close it up, because then these top corners will just get knocked off by the bearing as it all compresses. Kind of depends. You can try it with and without. And then into these bottom holes, I'm going to place some adjustment screws. For that, I'm going to use M6 grub screws, otherwise known as set screws. And they are short screws, come with a variety of tips. These happen to be points, but you get them flats and domes and different types. And I'm just doing a tight fit into the hole. I'm not convinced. You might need to replace that with a heat insert. For now, I'm just trying it this way. So I'm going to start it, in fact, with an M6 tap. Because I found when I tried to just go straight in, it didn't like it. And I want the end to be the tightest. So you just need to make sure you're squaring that way. Not going all the way through. That'll be enough for it to get started. I mean, as you get near the tip, it will just be biting into the solid plastic. So done like that, I think that's probably strong enough. It saves the hassle of another insert. Minor detail that in most of the design now, you lose access to that because the motor's underneath it. So things will have to be set up in advance or split access, but there's more sophisticated methods you can do, obviously, but this is just dead simple to get started. So that's not bad. That should be slightly proud, so there'll be a little bit of extra preload on the spring. Oh, I did do access holes at least. Still, got to remove the motor, so. Okay, very good. So, that is there. Okay. Oh, of course, forgot the bearings. So, the bearings have to go on here. We're going to need 20 for each mechanism. The size is 4.7 by 2.5. That is known as a 7/4 ZZ. 7 is the outer, 4 is the inner diameter. ZZ means 2 metal shields. You also get RS, which is for rubber shields. Okay, so so just make sure that there's not any swarf. Trap back here. Because you want the bearing split to turn very freely. 5 in there. And you want 5 in there. If you get it right, it goes easy. And as before, that simply clamps down. And that gives an exceedingly low friction surface against which our spring can be squashed. Do this in one this time. Ta-da! Just bet you can do that with the right little flip. Nice and tight. Okay, so that gives us that surface. These are 60, I believe. Yes, 60. Okay, so you have one bearing around the outside of the motor, have the torque output, and then we just apply a little bit of heat in here and in here before we put this together. That will just allow a little bit of give. This is just a plain clamp in. See, it's got a couple of imperfections actually. Just don't want anything getting caught underneath the bearing. A little bit which can stick up. Of course, always wear gloves when peeling. Try not to stab myself live on camera, because then you might hear a bad word. That's a bit stubborn. Might need a change of tack. Normally they snap off. If they don't, you have to trim them. That's fine. In fact, these ones you don't need to bother. These ones have been printed flat, so the circles are exceedingly accurate. The problem with these ones is that they might be a little bit tight on the height. It appears to be good. I think it's meant to be a 7mm bearing. Yeah, so it's a 7mm thick bearing, and the printer has opted to make that 7.2 mils because I'm printing in 0.4mm layers. That's actually slightly better. I don't know, means it goes on easy, but it causes a very slight interference against this, so always swings and roundabouts. So in fact the only one that needs to be done is this end, and that will be held down by this clamp. But for now, I'm just going to heat this and sit the bearing in. Messing up a bit. Okay. So spring goes like this, whichever has the most. Very similar, really. See how that lines up? Push it into there. Bearing goes on top. It goes there. And then whichever side of this is flattest. And if need be, you can just linish it up on an emery board, or in this case a diamond board. And that'll just take off any hot spots. Any high spots which could become hot when it's running, and then the plastic will start to weld itself to each other, which is not great. You can put grease. I tend to avoid putting grease because grease will attract dust unless you only work in clean environments, and then that will grind away worse than just left to its own devices. Now that does not appear to have gone all the way down. Yes, of course it won't, because the spring has to be compressed now. Okay, so the front of this coincides with the hole for that. You can see how that'll start to draw that together. Pull it together as much as you can. And the reason for that is to make sure that the thread engages cleanly. If there's any resistance at all, don't force it, because you'll just damage the threads. And that's not a good thing to do at any stage. So if need be, back off the other side a little bit, so you can pull these nearer into alignment. Start it off by hand. And that way you can make sure you don't accidentally break something. I wouldn't do it up fully tight on either side until both sides have been done. feels to me like that's actually hit the bottom of the plastic, so I suspect I've not made this implant deep enough. And that will have ramifications, so it's going to make it harder to get that bearing on. But we shall try. Yeah, I think that's a damaged one. I think I've accidentally put plastic up into the thread, so this one can't go deep enough. I guess I'll just have to make this screw a little bit shorter, or use a washer. So about 2 mil shorter. So there's a little lesson on the importance of good quality inserts. Nonetheless, if necessary, you can always add a little bit of heat to that to get the bearing, because that's come up a little large, I would say. You want some squeeze, but ideally you want it nearer to that. Yeah, it's going to be tight. All right. On the front of that is a 6812, and here you have 2 RS. So I guess an RS is just one rubber shield. Maybe you have an RS ZZ. ZZ always means for 2 together though, so not sure why it's 2 RS. And now our mission, should we choose to accept it, is to get that to fit onto that. Oh, well, that was easy. And that is just stupendous value for money. It really is. You can get these for €5–6. Hardened steel, precision. Usually people get very fussy about how you remove bearings, but one of the nice things about working with your main material being plastic is that things will go on and off without the kind of forces that will damage them. If you do this on a metal shaft, you will severely damage your bearing, assuming you can even get it to move at all, because the forces you have to apply to get it to move against metal are just very high. On plastic it's quite easy, you can just pry it off, which is good, because it also has to fit inside this one. Which is close, but there we go. Just need to get it lined up. Not quite is the answer. Close, but not quite. Well, I guess the other thing is to print a rig. Oh, there we go. So yeah, I think I might print up a rig which just allows you to screw that down and it will pull it in nice and easy. But it will go. Again, another test of your printer. Quite a long way down to go, so I will struggle that down. Oh, yeah, I guess you could use this in fact. Yeah, don't know. Anyway, that's go all the way down there. Don't use a hammer. So it's not ideal because it's not square, but you can inch it down like this. And the trick is really just to try and keep it even as it goes down. To keep the jaws more or less parallel. And try not to damage the inside too much. Let's see if I can devise a better way of doing this, because this is obviously not good. I think a printed screw guide. So the best you can say about this is that most of the damage is on the inside. When it goes, and it's fairly straight, it will just pop down. A little bit of damage to the inside, not too bad. Any other scrapes can just be repaired with some heat. And that is the bearing nestled down into the socket. I think this is about max speed. I think that will do, because well, that's attached to a limb. Small enough for walking. That's with velocity at 30 rads per second. Oops. Into its zero position. Here you can see the effect of the force on the hip joint going back into that spring. You can barely see it. There you go. And that displacement, or rather the rotational difference between this internal piece and this external piece, is crushing that linear spring. And causing the mechanism to store energy. Consequences of that are that you can actuate a motion for longer, store energy here and release it more rapidly than the actuator itself can achieve. This is called a series elastic actuator mechanism. And the disadvantage is that control is harder, because you build flexibility into the system. So up until now, it's been problematic. And the expectation is that more sophisticated control, i.e. simulation, modelling, reinforcement learning, all the stuff that we're now seeing making humanoids do amazing things, can overcome this. And that means you can use a cheaper system to generate high performance robotics. That is the aim. Mechanically I will finish it. All the bits printed down to the ankle. And I guess I'll publish it all as well, so you can start building one too if you want. You're going to need a bunch of motors. That's probably what's going to slow people down. These are what I'm using. and it's completely untested. So just putting that out there. But we're publishing the open, so yeah, why not? Anyway, the reason I started this was because I have received a new pack of these, and I have to put some in here, which means I have to take this to pieces. So I thought I might as well show you what it looks like when it comes to pieces and when it goes back together. To give some positioning, this is the right hip joint. So if it was lying face down, this is the front of the hip, but flip it over, imagine body turned over. And this will be different to the knee and the lower leg, because here the series elastic is attached to the motor and then drives a pulley, and on the knee and the lower leg it's the other way around. That's largely done for geometric reasons, but I think will work out better because I think you better store more energy in the lower part of the limb, the knee and the lower leg, and you'll get better precision up here in the hip and the yaw. Oh, rotation is also just direct. So this is the pitch joint of the hip, the right pitch joint, also known as flexion if you're using the FAR designation for flexion, abduction, rotation. It's what I call pitch, yaw and roll. So FAR or PYR. Right, so let's take this to pieces. Turn off the power. I wonder if I'd take it to pieces completely. I probably do actually. I want to get this out. I've got to take that out. Well, I might be able to pop it over. I don't know. We can try, but no, I think it's bad. Let's just remove the whole lot. Shouldn't take long. Right, these are M3. Oh, I haven't really finished screwing it in very well, have I? Still, enough to check that it works. This first prototype is being done in PLA Plus because it's a lot cheaper than carbon fibre nylon, which is what I'm going to do the rest of it in, or rather the proper prototype in, as it were. And it's got nice bright colours, which makes it easier to identify the bits. Bit misleading though, my bad. This should be green. This is bolted to that. This is attached to the motor. So that should be green, sorry. That's the slider. There's a bolt down there. These are M4 and there's a crossing M4 as well. It's actually quite stiff, it gets clamped down by the cross bolts which hold the whole thing together. So this becomes quite stiff, which is fine. And this circular series elastic actuator mechanism, so orange bit should be green, attached to that frame. Orange bit there attaches to the motor output. Spring between the two is what generates series elastic. There you go, see it better there. That orange bit is attached to the motor output. Right, got to get this off now. So there is a retaining ring down here, which I've only bothered to put 2 of the inserts in, but can go up to 8. This is a, what would you call it? Thin section deep groove ball bearing with 2 rubber shields, which is 2 RS. Don't remember the exact sizes off the top of my head. You can check all of that in the bill of materials. Again, it is a retaining ring, which also includes the teeth for the belt drive, MT5. These are 500 long. I tried to go for common sizes. And it splits apart. And what I didn't do is I didn't put the insert in here. Very good tool this, by the way. What matters is that it's TX Torx 6. There'll be a few part numbers which have slight variations, but very nice to use. Okay, just keep those like that. And now this is held together with a pair of M3s. One down here. And a long one up the top, which goes all the way through the structure. Now, there's a question mark about whether or not the motor in direct drive can provide enough torque. 120 kilogram centimeters, 12 Newton meters. Hold it for 28 seconds too, which means it can clearly go higher, but I don't know if we can change that in the firmware. Anyway, for the yaw, that's right on the limit, and it means the robot won't be able to carry anything for sure. So I expect to add a 2-stage, another belt to the yaw, the final release. And that mechanism will change the shape of this and will attach up here and do something, not quite sure what yet. There we go. So that is the guilty party. Doesn't look quite right. I think things have moved around a bit. Anyway. Oh no, that's okay. It's slightly angled. So there's various ways to put these in. These days I tend to use a soldering iron. That is the size of it. Oh no, sorry, my bad. Not that one. These are M3. This one. Let's just make sure. Yes, M3. Okay. So it's very simple. So it's very simple. You can see that there, very good. Just get a soldering iron, and you can get special tips which will make this even easier and more accurate. And as it heats up, make sure you keep it nice and square, guide it into the hole. Make sure it's gone all the way in. That's it. Of course, it's just to be careful not to burn yourself on the soldering iron, because that does hurt. It will take quite a long time to heal up as well, so it's very annoying as well. Okay. So always make sure your soldering iron is kept in a proper soldering iron holder, like that. Don't leave them lying around. And then we're just going to screw it back together. And that will pull the two inner structures onto the bearing. As you see, there is a bit of a gap there, which will close up almost completely. and I'm debating whether or not it needs just a tiny little cutout over there, but it did all go together, and that's pretty much at the level of the kind of variation you're going to see across printers, so limited amount of advantage to really getting into that. So long as this goes down tight, it should be okay. So you just want to start off all of them so you just want to start off all of them so you know that all of the threads are located before you start clamping it down, and then little by little just work your way around the frame. Yeah, see, that's what I'm trying to avoid. A little bit too much over here. Didn't do that very well. Ideally, it should all pour down evenly. Yeah, that's not bad. Plastic is, of course, rather flexible, so it will conform. And the fact that there's this bearing in there is really what's going to keep everything straight. Yeah, that'll do. Right, and also just going to check, arguably a bit late now, that this fits. Bit squeaky, but it's going in, and that's fine. Okay, right, this can now be reassembled, so always worth having a quick check. There's nothing stuck in your teeth. Put a lot of strain on the belt if there's anything stuck in there. Should be a nice snug fit. And, okay. So the pelvis itself is made up of 4 pieces: the crests at the top and the spars at the bottom. This is first and maybe second or third generation, but whatever, there's changes being iterated, and obviously the left side is missing, because I'm just prototyping one leg at the beginning to make sure. As a general rule, the first one to be assembled is always full of slight mistakes, and they go back into the CAD, and the aim is that eventually the mistakes become so small that you don't notice the corrections, but no design is ever really finished. So that simply presses down onto there. This is the assembled series elastic actuator unit on the output of the cyber gear. That will engage, and in order to accommodate these clearances as this moves around, it wants to start off with them basically in line. I'm going to engage that belt. Again, just quick check. Remember, it should be green. This is screwed to that bit. The connection between that bit and that bit is via that spring. Okay, so make sure the belt isn't raised up or caught on anything. In the sliding bearing, there's a sliding bearing up in there, which can be adjusted from underneath and locked off with the side ones, but for now we're not doing any high stress stuff, so that simply has to go into position, keeping it as it was. Oh yes, so in fact for tensioning you've also got these 2 screws on the side. That one is a bit hard to access, so of limited use. I'll see if I can, so I don't see a way to do that unless I come down from above. guess it can be used later. Once the motor is roughly secured, and you can quite happily pull this around by hand. And at least before the rest of the leg is in, you can get access to that. Very good. So these will take most of the up and down force, translational force. These are only friction, so friction is very susceptible to movement. And there you can see, that as that rolls back, the mechanism moves out of the way. Just to create that gap, I think that could possibly be a tiny bit here. That's not bad. I guess there must be a perfect number of teeth. But that'll do. There's a bit of range, bit of marginal error. Okay, so that's back in. Again, to make sure there's no swarth. Use the retaining ring in the centre. I might add some alignment marks, although this screw has to be in the centre like that, so it's not too bad. Clamps down. Clamps down. And then just tighten these off. And there's space for 4 more for now. That will do. And if the belt does not run true, then that's what you can tune out here. You can go up or down by a few degrees, and that should be all it takes. Show you that under power again. Plug it in, give it power. Why is it not moving? Try again. Yes, you can hear it start up. That is one thing I think about this robot. I think it's going to be quite loud. Not least because all the frame is open, of course. But that's okay. I think that's just something to get used to with robots. But as they get more expensive, they get quieter. This we're aiming to be very, very cheap indeed. It's almost entirely 3D printed. Bearings like this I find shockingly good value. And these motors in China are only $65. They're going to cost you about $110 everywhere else, not including tariffs. That means you can do the whole robot, the whole humanoid, with hands, if you use the cheap servos, for around, not including a computer, not including a 3D printer, for around $2,500. Bill of materials, not including tariffs. And of course it'll have software by Le Robot and also Isaac, so NVIDIA, and just, let's get everyone building robots. So that is the hip joint, the hip pitch joint of the Hope Junior. The arm, in fact, is already out. So you can build the arm and the hand right now, but there is a new release. There is a new release coming in just a few weeks, which will be substantially stronger. So particularly the servos. I've upgraded all the servos and the big one in the shoulder now. So don't go buying anything until, and if you want to build a new one, just wait a few days. Right, so that is the hip pitch, and we are now going to add the yaw, which I have not done before, so we shall find out if everything fits or not. These screws are the ones which are going to secure the motor mounting plate. squeaking is not a great sign, but as long as it turns, it's okay. It means the alignment is slightly off. I'll put some washers now. That will help spread the clamping force from the bolts through the plastic. Your motor at the moment is direct drive. There's only two direct drives, the yaw and the roll. For one leg, I think it's okay. By the time you've got the weight of the whole robot, I don't think it's enough, so there will be an upgrade, functionally at least. I think it's going to look a bit uglier, but there'll be another belt system and the motor up here somewhere, which is okay, but it means it won't be able to bend backwards very much, except at the waist, of course, which is it can go all the way around. Right, so this is like the other units. It's clamped together from 1, 2, 3, 4 bits of plastic itself. There's 3 bits for the motor mount. I have filmed that so it will appear somewhere. And with power, doesn't feel like it. Not quite sure how to connect a new motor. Yeah, there's definitely something wrong I'm doing. Got to disconnect and reconnect for it to work. Whoa! It moves fast when it goes. Crikey. Watch out for that. Yes, that was set to go fast. So that's something to bear in mind. When that's inside a robot, if you initialize it incorrectly, it's going to move real fast. Crikey. Yeah, that is quick in direct drive. That is really, really fast. Okay, there you go. So, and there you can see how now the motor is locked to this. Not sure how strong the PLA is actually going to prove to be, so I'm not going to push that too hard. But that is where the energy will be stored. Right. Can unplug that. This fits into that bearing. This screws onto there. That should be it. So there's a clearance there. Okay. Slightly tight those holes, but that's not a bad thing. Not really strong enough, I suspect. But this draft is just about checking everything can be physically assembled rather than whether or not it's all really strong enough. Got my washers. The strong one will be the next one, which I will do in the carbon reinforced nylon. Okay. So I think that looks far too fragile now I see it, but everything clears, which is what this build is about testing. So now we have, if that's your fixed pelvis, pitch or flexion, your otherwise known as abduction. 2 joints. Up, up, up. For those of you who remember Sesame Street. Right, straight on to humeral rotation. Is this going to be humeral in my legs? Probably iliac rotation in my legs. This design will serve as the basis, though, for the HOPEJr arms, because the dex hand is just the right size to fit the Hope Junior legs, which is a happy accident. So far, I'm not bothering to test these as such before I assemble them, and the 0 position have to be set fresh each time, so that is a bit of a limitation. Now there was one, yes, a couple of things on this one, so I've changed where these locating holes are in order to improve the positioning of these retaining holes. So that ends up there, which means I've got to move one to there, and remove this one too. And these are held with a bit of Loctite, so they should just crack and then suddenly start to come loose. If they don't, you can use a bit of heat to loosen off that little blue glue there. That one stays there, and this one goes as well. You can see, in fact, that is here. So at least there's still 2 of the original screws holding on the, at least there's 2 of the original screws holding on the back, and that will prevent rotation, more or less. Right, very good. So now I'm going to need some longer, need at least 5 mils, maybe 6 in there. That's what, 8, 14 or 16s, M3, what have I got? I do have some 14s actually, not in stainless though. I've got some 16, here we go. Yeah, 12, 14, oh, I've got many sizes. So in fact I've got 16, 14 and 12. Let's start with the 16, see how that feels. And looking at it, I do believe I made my favourite mistake, yes. And that is that in order to access these, I have to disassemble that. So assembling the first one, this is generally the case, but each time you check something works, you'll very rapidly have to undo it. That's not such an enormous problem with these robots, at least until the wiring is done. Once the wiring is done, it's going to get much slower to do anything. But for now, design. Something catching that? Feels like it. You can get down behind here. Generally better to prise than push. And usually you can walk things out. Okay, so this motor in fact fits into there. Okay. To access all of them, in fact, you've got to take it off this completely. So going back another step, even. still, you get to see how it all goes together, I guess. If you get bored of doing that, you can always do this. So that will release that from there. Now you can see get jammed in. Okay, so that's how it all splits to pieces. Where that goes back together, or look at this first. So there are 3 pieces which lock onto a bearing, which screw onto the motor. And in fact, I'm going to screw all of them for more strength. See, that's coming loose already, so that's a concern. You might need a drop of glue. Because you are screwing onto plastic, the amount of clamping force you can generate is quite limited, so they're more prone to shaking through. So these are 3x6 countersunk. Yes, that's easier. Because they're countersunk, they will sit into those holes. Actually, that is fine, because that's just the key. That's not really taking any load. Okay. Okay, spring is into the bottom of that. Has 3 adjusters underneath it. There are 20 bearings on those 2 M4s. That presses into there. That goes, oh, this bearing goes on there first. That presses into there. This presses onto here. And there's one which is slightly flatter, which has been sanded, and that goes onto there. And you screw it back together. The actual bolts it attaches to are in here though. So this needs to be screwed on first, which is how we started this whole process. Right, so that was the question, what size do we want? That's obviously ample. That is a 16, so yeah. I suspect a 14 is a touch on the short side. Yeah, no, it might be okay. Let's try 14. Fourteens may be harder to get hold of than 12s, however, so maybe a 12 is the best. Okay. So now we have a 12. Is that any good? Yes, all right. So 12s will do it, and 12s are common, unlike 14s, which may be a struggle to find. So this motor can be screwed on like so. Now again, this is only PLA, so the performance I'm expecting out of this is fairly limited because it will simply start to melt the structure. These motors apparently will get hot. So for this first draft, it is just about whether or not it's possible to assemble everything and it all moves like it should. I've also made a lot of guesses about the torque requirements. The belt's up for torque and they do make it very tunable, but the design I have gone with is the maximum I can fit inside my printer, which is an old up box. It's the wrong size, isn't it? Naughty, naughty. With things arranged like so. And the standard lengths of belts, I try to use 500s and 400s and 300s and standard lengths of belts because again they're going to be cheaper and easier to get hold of. So this in the hip pitch, for example, is 500, the knees are 400, the ankles are 500, and that does have some restriction on the range of racers you can get. But the target is that it is about half, I keep getting the wrong size ones. No, that's correct. Half of the size, half the weight, thereabouts, of the Unitree, and a little under half of the torque and power. So the performance should be fairly similar. Okay, one more. Now the other interesting test is that this will use the motor can itself as part of the structure, which is very efficient in terms of design in things like motorbikes, but somewhat untested. And it may cause distortion of the motor, so we shall find out. I hope not, but you never know. Okay, so that is now a motor screwed to the adapter. I set that up, I think, with the wires on the inside. So yes, this is going to be forwards, so yeah, like this. And then that can all be screwed back together again. Yes, because the access to the motor is clear. Right, so this is almost certainly better if started by hand, because if you cross thread one of these as you're screwing it in, you can damage the threads and then you're going to have to replace one of these, and that's going to be a pain. You should better get it started. This is where you want to be careful. As you come up to this part, if you just blast that through and you don't get the thread dead clean, you will have damaged threads. Probably okay on this one because it's been assembled once or twice before. But as any engineer will tell you, every 5-minute job is one broken screw away from being a 2-day ordeal. 2-hour ordeal. Okie dokie. So as those tighten up, it will compress the spring. And you'll get a lot more feel doing those last few turns by hand for sure. Okay, right, so that is hip roll now attached as well. We can reassemble the yaw joint. pelvis, pitch or flexion, yaw or abduction. Well, abduction away, adduction towards. Right. Okay, this was up to now. That's hip pitch, hip yaw. This is the motor direct drive. So more or less like this one, except circular for rotation down the upper thigh. This is known as flexion or pitch, abduction or yaw, roll, F-A-R-P-Y-R. I've always done pitch, yaw, roll, but people are talking about flexion, abduction, or adduction, and roll. If you're getting anatomical, adduction with a D is towards the centre line, the sagittal plane, and abduction is away. That is the pelvis and start of the hip for Hope Jr. One of the nice things about the high quality PLAs is that they peel off supports very easily. Just want to have a quick word about supports. Wear gloves. Might seem like overkill. If you're going to use sharp tools, wear gloves. Tools I like to use are a paint scraper, an old knackered pair of side cutters, screwdrivers, and most of the designs will feature large flat planes. You should be able to get underneath them. And just work your way around. If possible, just peel away what you can. And if your printer is set up well, it should just come off like that. Always a little variation. There we go. This is the retaining collar, which will hold one bearing and which will secure one bearing to the motor. And you just want to make sure that any little bits left hanging are popped off. Any bits of damage can just be pushed back. Make sure the bearings can go down. And if any bits get caught underneath, you can just use a little bit of heat. Make sure everything's handy. Excuse the noise of the builders. So there's a flame there. And that way things will just get soft and can be lifted out of the way. Let's come out of gas. Beneath that is the knee series elastic actuator. This is slightly different to the hip pitch. Now this is very different to the hip pitch because in this version the motor is driving the pulley, which in turn will drive the series elastic actuator mechanism. So this should make it less stiff but store more energy, and we'll see how that works out. And then underneath that is the lower leg, and at the bottom of that is the ankle joint. So we shall put all of these together now and see how that works out. Okay, so got some more hot inserts to go into here. I'm going to make sure that everything lines up by having some long screws ready to go. Just going for about 80. Make sure your holes are drilled out. And not a good idea to drill towards yourself. But hard to show on the camera otherwise. So then it should be easy to pass those through. Going to get that into position and press it with heat. I'm going to make sure that it screws in to that. Just take a few seconds to heat up. Push it into the hole. Make sure that can screw into it. As you can see, in fact, it's pushed it out of the way, so that has not worked. Oh yeah, so the end's got blocked out of plastic. Interesting. In fact, another way to do this, it's maybe more reliable then. So the other way to do it is to pass the screw down inside. And then it's going to take longer to heat this up, but it will mean that any molten plastic won't get trapped in the centre. So it's a pair of pliers. Heat that up. Pull that in. Now you can be sure that that screw can still go into that insert. Repeat for all of them. So I think this is the recommended way to pull in these inserts. Otherwise you risk them getting blocked up with molten plastic. You need to get that really quite hot. Try and show you the next one. Try and keep this one in shot. So you can see the flame there, quite a serious flame. This is an M4, we're going to have to heat it for about 20 seconds. Then with a pair of pliers, pull it in. Hard to film. Make sure everything's lined up. Okay. So, as always, when using pliers, never pull towards yourself, because if you slip off something and you bash yourself, it's going to hurt a lot. Okay, once those are cooled down, we can unscrew those and we can assemble this mechanism. Oh, right, no, in fact, so whilst that cools down, we can put the front plate onto this motor. And that is in some ways just a simple plate, and its function is to hold a bearing. So the way that this works, so there's a groove there which engages, there's a groove here which engages, those two come together, and then this piece is a key. And when that is screwed onto the motor face, that will hold everything in place. Doesn't make any difference at all which way around it goes, except that this hole here is the largest and the easiest to fit, so traditionally, as it were, I kind of put that on there. And then just M3x6 countersunk. Just do them up loosely at first. Just want to make sure it doesn't pop up like that. So apparently we're not going in. Let's try that again. Okay, make sure they actually go in a little bit. And I'm just going to use 6 for now. No, let's just do more. Probably best to make that as strong as possible. Yeah, I should definitely use all of them, because all of the force of the leg is going to be pulling on that. So in fact, this one will probably need to be strengthened. And tighten all of those up. Okay, and that attaches a bearing to the end of that motor. Bearing is going to be housed here. So first thing is to get all of these out. Just be a bit careful at first. Plastic will grab. Visual inspection, pretty good. Okay. So to the motor we'll attach this part. It has M4 cap heads running the full length. No, wrong one for this, sorry, my bad, it's this one. For the rotation, it's this one, it's the shorter one. So for direct drive units, they're shorter and they don't have the hexagon on the end, because the hexagon mates with the pulley. So that one's for the knee, this is for thigh rotation. And they're slightly too long, unfortunately. That's an 80, I think it's 75, let me double check. Yes, indeed, they are 75. In my case, if you cut them off, 74 mils. Yeah. And that will both anchor this torsional part to the motor and give some width for the bearings to locate. We need 20, 4x7 by 2.5 for each SEA joint. bit of practice, this can be very pleasing. Five in there. Oh, almost. Oh well. Went so well the first time. Just use a screwdriver or something. And make sure that they don't pick up any bits of swarf. That's not what you want. Let's see if we can get it to sit in this tube nicely. Not quite. Right, made a bit of a meal of that. Anyway, put the bearings in the slots. Take your cap heads, pass them through. I mean, force them into the holes a little bit, so that way nothing's going to fall out. It gives you your bearing surfaces, and as the motor can be set to any position, doesn't matter where you put this in. It's not engaging where I've gone. Make sure you get it in 2 screw holes, otherwise nothing will happen. These will screw down and be a tight fit in these holes at this end, and that will help to reduce how much they shake loose. They want to be done up nice and tight. And to do a bit more force, you can always use an Allen key with a handle. Bear in mind, these long ones are designed for undoing bolts, not doing them up. So don't overdo it. Okay. So, back to pick up a motor. Going to place a spring into here with as much of the flat in the right place as possible. Have a bearing. Push that down onto there, and that will form the thigh rotation joint. Into here you now need 60mm M4 cap heads. These are M4x60. And if necessary, drill these out as well. In fact, looking at it, I could do a bit of finishing. As you see, as soon as the flame touches the surface of the plastic, or it's gone a little white from being peeled, it'll return the colour. That'll also help seal in any loose filament. No, in fact, that's not 60 here. That's much shorter. What length are these? These are only M4 by 35. M4 by 35, which I do not have partial. Now, careful not to break this off here, particularly in PLA, that's not particularly strong. So I didn't really spend a lot of time on this. Might be worth, but I think it probably is. Heard a bit of a crack there. Not really going to be a problem for the carbon. Definitely a problem for the PLA if it cracks. It doesn't help if there's little bits of plastic in there. So before we assemble that, I'm going to put a bit of heat into this as well. Make sure this bearing can sit down there nicely. That will just allow any high spots to be flattened off. Let's start looking at this. This will need strengthening up a bit. Which in this version I can do quite easily, I think, just by making these a bit longer. Might add something around the back of this to make that stronger looking at it. But for now, we shall just keep assembling and see if it lasts. Bits. Okay, let's try it again. Squeaky one I like, but that seems okay. And I know why. So angle slightly off because they need to go in a little bit together. Okay, so clearly this is the weak point at the moment. I'm still squeaking a bit, but we can live with that. Okay, finish by hand. Okay, just going to clean this up as well. Yes, in fact it has. It's broken already just back here. So this is not strong enough. Okay, well that's easy to fix at least. So I shall make a clamp for this one, and I shall modify the actual print before I release the files. Yeah, that's obvious. Okay, shouldn't be a problem with carbon as much, but PLA definitely not strong enough. Right, we shall keep going all the same. So that is now 3 degrees. Hip, pitch or flexion, yaw or abduction, roll. Okay, next is the knee joint. Okay, so I've just made a quick repair with a longer bolt while I print a new one of these with more reinforcement there. So we can replace that when it's done, but for now we keep going. That means the knee SEA needs to go in here. That's a slightly different setup. On this one, the torque comes in through a pulley. And there's a smaller pulley which attaches to the motor. This is a 3-to-1 20 to a 60, and quite curious to see how much difference that makes to these, because it will compress it 3 times as hard as it can in the hip. So I'm expecting to put quite a lot more preload on this, and I hope it works out okay. Just partially tap these to get them started. It's 110 newtons per millimeter on these springs. So even a little bit will make quite a lot of difference to the characteristic. Okay. So we have a bearing in here, which goes on the outside like usual. This is the ankle one. This seems something. Oh no, that goes like that. Okay. The key, as always. Press and keeps everything apart, and then this bearing goes on the outside here. And that will fit this. Like that. Okay. So, and then there is a retaining ring which goes here, and that will screw down and keep that bearing in place. So this is taking M2 size. Like these. Again, can just be inserted with a silver line. Slightly thinner in the one side. That will just allow it to guide in easily. And with 3D printing, of course, there's very little penalty for adding extra holes. So I've tended to use 16 holes everywhere. It gives a bit of spares, gives a lot of extra capacity if needed. I feel it probably slightly improves for print as well, because prints are not great at having large expanses of identical or uniform material. I'm sure that will do. That can go on top. And just make some very short ones. These are M2x6. Oh, not M2x6. Those are yes, those are posi. Not a fan of posi, so we shall use M2x5. I don't like posi because posi is designed to eject the screw. So you have to apply a lot of downward force as you screw things together with torques. They are self-gripping in the sense that the sides are more or less parallel to the long axis of rotation. So you don't need to push down hard to get a lot of force. Like many things, the 10 at the best is not what is the standard. But I plan to make it the standard in robotics. And good practice, as soon as finished, close the lid. So again, just put enough in to make location. Rather to ensure they're all located cleanly before you screw them down tight. Okay, so this is what will attach to the inside of the knee joint and support the series elastic actuator. It's going to go like that, and this spring now. Okay. Yes, so same thing here. When this attaches. Okay, so this goes around like that. So some heat inserts into there, that will screw onto there, and then we can assemble it, and that is as far as I plan to go today, so that'll be nice. We can actually finish something. So we need 4 of those, 4 of our long M4x80 screws to make life easier. And start by cleaning out clearances. That swarf. Make sure these can all go down nice and easy. Pick one to start. Screw on the insert, heat it up, stick it in the hole. It's not rocket science. It's robot science. If your threads have got filled from doing this before, just use a scalpel to cut out any residual plastic. Or if you have a wire brush, that would also work. troublesome. You want to make sure that there is some sticking out the end. Sure that this is flat. See how accurate your printer is there. In my case, not very. Okay, flame ready. You want it hot enough that the plastic is going to grip to the threads. So you'll see the brass just start to change colour and start to oxidise. And it's getting up to red. Red's probably a bit too hot for PLA. But it does want to go in relatively easy. Just apply a bit of pressure. And if you're impatient like me, you can use a bit of free spray on it. Sometimes you might get a bit of material welching up, and just separate that with a knife. And a bit of flash, not a big problem. Be very careful with scalpels, they're very, very sharp, and they're very good at cutting people. Crikey, that one went down further than I expected. That's probably no bad thing actually. These ones should be nice and deep down. And potentially there might need to be bolts that actually run into this. We shall see what happens as we start pushing up the loadings. Should be fun though. So, prepare the other side. So the plan is to stick this one in and then screw that one in and make sure everything still fits. See the brass start to change colour with the oxidizing. Make sure everything still screws together. Each time you do that, check all your alignments, make sure everything's square, make sure these all match more or less, and just keep pressing that together until it's cooled. Probably putting these in a bit hot, but it's better to go in a bit hot than too cool. Not perfect, but not terrible. 2 more to go and we're done. that one I'd say didn't go quite deep enough. Kind of rushing this a bit, so that's my excuse. This time, just make sure everything can screw down. Okay, last one. Okay, good. And that's not a mega strong, but it's not an unreasonable attachment to the top of this. 4 bolts, some cross pieces, might be reinforced. We'll see what needs to be done as we start to turn up the power. And then this is a cross hole, and that will be used to clamp the motor in place and then run the belts down to the ankle. So for now, we're only going to assemble the knee. Lengthwise, it's going to be 60 again, isn't it? Yes, this will be 60s again. Check clearances. Possibly easier to add some of these inserts now. But I don't think I'm going to necessarily need them for this particular model, so I'll just add a couple. Come out of here. just in case we need to later. So 2, 3, 6 of those, 4 of those, another spring, put the spring in to maximise the amount, then 2 80s, and then this will need again. Make sure there's plenty at the end of this one. Push that in. Again, make sure there's plenty of thread, because the screw cap head is going to come through from the other side, come through from that side. By eye, make sure those are well lined up. Make sure they're pretty much in the right place. They should be fine to go down there and clamp together. Another 20 bearings. You will get through a lot of bearings building this robot. See if we can do it properly this time. And make sure we don't drop out. So worth getting the bearings right the first time, because they're a pain afterwards. Use a pair of tweezers if you've got them. tweezers. So sometimes you're just going to need a pair of tweezers. Okay. Now the torque is transmitted onto this from this pulley via the belt and onto that hex drive there. So as you see, these have created a bit of a mound, so I'll trim that off so it grips properly. Say that the spline is not quite deep enough, so I shall improve the fit and the depth of that. Yeah, that's not great actually. That's really risen up a lot. Okay, I'm going to do a bit of finishing on that one. That basically means pushing this in deeper and then trimming off the excess. Make sure it still grips. So I'll make that a bit deeper. The spline does not grip as well as I had hoped. And once again we can insert our bearings. I'm just going to screw it from above to make sure I've recut the threads correctly on the other side. Okay, very good. So that's now flat, that's all assembled, bearings are all free running. That will screw down onto there, so into these holes, I'm going to put some more inserts that are really to be precise. I made the holes too small, getting quite a lot of fat coming up, it's a bit annoying. drill blade somewhere carefully. Don't just be chucking those in the bin. Brand new scalpel, should be no problems. Take extra care not to slice yourself. A little bit of hash on. Still, I think it will be enough to give movement, and we're really only after movement in this one. 2 to go. So just push it in. There will be flash. Try twisting to help reduce that. Just trim the excess. I think I will work on a way to make that better. Okay, not brilliant. Might even put a real spline on there. Those inserts are a pain, that needs to be done better. Nonetheless, it's a reasonable start. Yes, definitely. Okay, still, and now that will suffice. The motor itself is held by a clip which fits over the back, screws down and fits into this channel here, where it can slide up and down a little for fine adjustment on the tension of the belt. There's a cross screw which goes through here and some kind of tensioning mechanism which I still have to work out. For now we should be able to assemble it and just get a rough feel. I've had to remove the screws which hold that in place. So without too much ado, we shall add these back in. There are some 20s for the front. And the rest are 16s. No, actually, I think it's a 12s. No, call my 16s in the end for this one. No, that size. That's a shame. right up and down in there. Across here you need 65. Okay. To this, we'll screw this pulley with M4. I'm not going to draw this for clearance, in fact, because it'll grip better. 4x20s. Probably easier to put this on first then. Also possibly easier to do it with the motor powered up, because then it wouldn't move. And one more. I'm more curious about the fit of the belt at this point than anything else. Because I have worked out the distances by calculating centres. I've gone a bit tight. But there's no guarantee how well it will really fit until the belt is on and we're trying it. That's a 60. That's a 65. Yep, okay. Okay, so the series elastic actuator unit itself. This has M4 by, I guess, 12. I think 8 will do. I'm pretty sure this is going to be quite a lot of reinforcing. Okay, so there is a bearing. It's gone. There. So this will go like so. Longer than 8. Let's go 12. Up. entirely happy about going into there. Yes, there's some plastic in here. So need to be a lot more careful putting in these inserts, as if plastic does get in here, which this one has, makes it quite hard work to screw in. On the plus side, it means it won't fall out accidentally. Clearly more can be done to improve the way this all goes together. Both in terms of accuracy and strength. Particularly the fit between the spline on the end of the output shaft and the pulley itself. Some washers might be a good idea as well. But for now, just want to connect those together. That's actually come up pretty square. Okay. So, more bearing. Just be careful to clean off any bits of swarf. Again, I'm rushing a bit, so I'm not clearing up as much as I should do as I go along. That will go into there. That will press into there. That goes on like so. That will go like that. I can see that this is going to have to come off to access those screws, and some inserts need to go into here. These are M3. Push those in. Bear in mind, I'm already printing the replacement for this part. I'm not sure I need to do all of these, but it's quite fun actually. Okay. Now this can attach to the lower leg. We clamp it all together. So the pulley is on that side, so like this. And that's one. Appears not to have gone in, or it's poured out of the insert. Or it hasn't reached far enough. I suspect it hasn't gone enough. So let's try a slightly longer one. 570. These are all 60s. 70, 65. That's better. By hand. Okay. Now, in fact, I'm going to remove this. And now this will hopefully press easily enough into this bearing, and then this can be screwed on. It's not an entirely good noise. Very nearly. So I suspect in fact the real purpose of this is to allow this bearing to be pulled in by screws. Okay. As it happens, I think, yeah, this is moved, so it's a bit tight. It's a bit tight. Okay. I think then this is as far as we will get today. Because my efforts to push this in are simply pushing this bearing up. And now it's got wedged in there. Okay, so this bearing actually needs to be retained properly before that one tries to go in. Here, something hits. Oh yes. So there's a slight fouling. This is printed now in PLA+. I incorporated the reinforcements for where it clamps onto the roll motor. And this is the extra clearance which was put in to avoid the knee SEA. Peeling, as always. Wear gloves. Something tough on your hand which doesn't hold tools. Something puts a grip on the one which does. And if you can find it, probably a good idea to have something with a bit of back protection as well, because sometimes you're going to slip and hit yourself on the print. Or at least I do, but I tend to rush that part because I find it a bit repetitive now. So we shall see how this peels. You usually start by finding an edge, getting a little bit of space underneath, and then you can get in with a blade, like a paint stripper. Always the rule when working with blades is do not push towards yourself. Yeah, sometimes get a little bit bending up. Just on the other side. So find a little gap, get underneath it. And ideally, it will suddenly crack off nicely. This one apparently is bonded a bit at the top, so such is life. Coming from another angle. Well, let's hope the rest of it peels a bit easier than that. Here, of course, there is a little retaining hole into which I can put a screw if necessary to keep the bearing from popping out. Now, the curved sections, depending on how exactly they're done, you can remove this part. You could go reaching in. And ripping it with pliers. Sometimes it's better to keep it, but usually not. Raised a little bit here. So you see this support's pulled away from the bed, and that will cause stronger adhesion. This one's actually quite difficult to peel, I would say. Some of the other colours and brands, but the colour does seem to have a big role to play in how it prints. I presume something to do with the properties of the pigment. And the flip side is if it doesn't adhere well enough to this lower layer, then your flat surfaces will not print flat, they'll have ripples in them. So always a trade-off. Okay, that's really what you want. It should just pop off like that. Much better. Now we can try and get underneath this curved surface. This is a clamping hole. And the trick here is just not to damage the surface you want to leave intact. You see I've broken tools. You can always repair that with a little bit of heat. Not bad, just one broken thread over here. So stick that back. And gas torch. Not going well. I'm just going to get rid of it. Nonetheless, you can see the effect of heat. Just seal that top layer. And clean up little white marks which are left when the support cracks off. I think one day there might be a whole industry of finishing prints, because this outer layer is where the most stress is taken. So if you can improve that outer adhesion and make it a nice strong skin layer, the whole structure could be significantly stronger. Anyway, not something which is showing up at the moment. I'm going to crack these last few bits off, and that will be a new thigh section. Oh, yes, I mean, sorry, of course. Probably a screwdriver. And of course, actually the tricky one on this one is the bearing housing. Okay. That feels very unfortunately like this is all welded on. That is going to be a real problem. Well, it's going to certainly slow things down. Not sure why that's happened. Possibly the support lifted slightly during the printing. that's coming out from the inside. Let's see if we can just get an edge up. In a way, this edge is not so important. As long as this inner bearing edge is clean, then we're okay. This is by far the hardest peel I've had to do of the lot. All of them have been using this, so I would say that is probably due to the plastic. Okay, so in a way, that's the important one. We've got the bearing surface, which will keep everything accurate. Because the real advantage of 3D printing is that it is incredibly accurate for the cost. You'd be looking at 10 to 100, maybe even 1,000 times the cost to have this CNC'd in metal or made by some other process to this kind of accuracy. Astonishing accuracy, 3D printers, especially for the cost, and generally very reliable. So I guess if need be, you can use what would now seem like old-fashioned methods of subtractive manufacturing to remove this bit of support. Shouldn't be this difficult. Something is slightly wrong in the settings for blue PLA. But as you can see elsewhere it worked. So maybe the bed is not as level as it should be. I'm using a very old printer. If you've got a more modern one, it will do a lot of self-leveling for you. So this is kind of a problem of the past. And I shall see you when I've finished it. Okay. So that was much harder to build than it should have been. In the end, what matters, you've got clearance and not too much damage, and that this inner surface is okay. I'm going to clean up the rest. Something to do with the colour blue in PLA. I'm not entirely sure what. Into that we will place a large bearing, which is 90. Black and white. Yeah, that's good. So 90 by 70 by 10. Also known as a 6814, and 2RS means 2 rubber shields. You can also get ZZ for metal shields. These are incredibly good value. I get these for, I don't know, I have to check exactly, but around €10, $10 delivered on from Ali. Remarkable value. This presses into here. And the key for getting bearings in is to make sure that they go in dead level. If they go in dead level, then they're generally okay. I suspect some problems being caused over here by this little raise. If they go in at an angle and start to jam, then it's going to be very difficult. almost there. So if you put it on the tabletop, you can keep things more level. And the obvious thing, of course, is I'll make up a tool. So you can just screw it down calmly and gently. Right, I'm going to finish it in a vise. And the other way, which is very effective, is if you have a second bearing, and you're generally going to need to buy spares, and then you can use some kind of clamp like this to just force everything in. Or at some point I'll make up a tool. But this does the job pretty well. Tricky with only yourself, but handy if you have a desk vise for a lot of reasons. Okay, so that now provides essentially a frictionless joint. It's actually 0.005, but there's quite a lot of resistance from the grease on these ones and the shields. But there's almost no stiction, which means the force to get started is very low indeed, and that's very important. Last thing to do is put in our heat inserts. These are M3, which are going to go in with a soldering iron. These are M4, which I'll probably put in using the gas torch because they have a tendency to overflow, and that will make it harder to then align the screw, or rather the overflowing will tend to jam up the hole in the middle of the insert, and that's not going to make it possible to get the screws in afterwards. So inserts are fine if they go well, they're a pain if they go wrong. So it's worth getting them right. Use a 4mm drill to clear this hole. Drill to clear these holes. Okay, there's also these adjuster holes for the spring, and these just get started with an N6 tab. But not all the way through. And that way the threading will be stronger and it won't shake loose. Well, these are actually a lot deeper than these, a little bit more. Just until that tip is starting to poke out. And just keep your swarf out of the way. Clear. Okay, so these ones are very straightforwards. Very quick. There's a slightly narrower end. There's a slightly narrower end which is easier to get into the hole. Will help with accuracy. Accuracy of these is not super critical.
It's a bit of clearance on the other hole. The accuracy is really from that raised edge above the inserts. Might raise a slight edge. If it does, just trim that off with a sharp knife. As always, do not push towards yourself is the rule with knives. It's a bit high, you can just push it in a bit more. The main thing is that the hole itself is not obstructed. It's easier to cut when the plastic's pulled down a bit. It's probably worth spending a little bit more time getting these right the first time and all this reworking. Nonetheless, not a big deal. Not super critical in terms of the accuracy either. Okay, that'll do for now. The M4s are a bit more involved. The principle is the same. And what matters on these ones, if you push these in from this side, there's a chance the hole's going to fill up with plastic and then you won't be able to assemble it. So for speed, I use a gas torch. And you get that until it's just starting to show a shade of oxide. You've got a slightly darker colour, and you can quickly pull it in. Smooth all the excess. And if you're impatient, you can spray with some free spray. But that will actually then bond to all the plastic. That will actually bond to the plastic. And that will help reinforce the structure. Okay, same again, 4 times. Notice I've done these upside down. It would be better the other way up, actually. Yeah, it would be better the other way up. So you actually want the narrowing to go in first, of course. So I flip that round, and now the risk is I'm going to burn the plastic because I reheat it, so I need to be a little bit careful with that. This way you'll maximise the gripping force of the insert. Yeah, that's probably better, that one. I think I was slightly overheating the first ones. And one more. And last one. Okie dokie. Oh well, it will do, I hope. If not, if this is still not strong enough, then I will add reinforcement bars across here which longer screws can go into, and that's why this now has a flat aspect to it. By doing it this way, you ensure that there's thread all the way down to the insert, as if you push them in from underneath and you raise up any plastic in that hole, then it'll be very hard to get the screw in. Okay. Any last finishing with the heat, torch rather. Right, so now I'm just going to replace that in the main structure. That will allow the leg to come apart. So the pelvis and the hip can be put to one side. Take out the carriage tailing bolt, take out the motor on the carriage, take out the belt, press that apart, and reuse the spring, of course. So you can see where it broke there, and you can see where it was fouling there. So the new one, as a comparison, I've gone back to the flat bottom, which is the standard design, which is at least tested to some extent. And if need be, it can be reinforced more. I've also made the bottom plate thicker, and I've just added that clearance in there for those screw heads. It's actually the knee joint, of course. We can check straight away. And yes, hurrah. We now have full movement at the knee. To access these screw heads, I have to undo the pulley. You can see the hexagon locking, and all that has to be done is that gets screwed in to these holes here. And those are M3 countersunk. Those are M3 by 6 countersunk. And the way to do these is to put them all in just a little so everything can start to locate, and then screw them all down tight. just finger tight will do. There's no point doing more than that because you are clamping plastic to plastic with a metal screw. Countersunk will help spread the loads, and you're much less likely to get binding. The problem with countersunks and other kind of non-standard cap heads, this is a standard cap head with the standard form M4 and M4. Countersunk, button heads, all these other type of screws, you have to go down to a smaller Allen key. And metal to metal, that can definitely cause problems. If they jam up, it'll be very hard to get them out. But in plastic, it's generally not an issue. Okay, so that will secure the knee. And the leg is stopped from going straight by this, which is not great because you can get your fingers stuck in there. So I'll have to have a think about what can be done to prevent that, maybe an extra shield or something. But for this version, like a kneecap, I guess. That is the leg angle it can go round to. .90 to straight. So the spec is that it can move around and climb upstairs. 90 degrees is enough for that, I hope. Any more than that starts to become very difficult to accommodate with the geometry I've got. And knees, and human knees, from this point onwards, we actually do a completely separate rolling action. So the way around it is probably to add a secondary bearing, which is not main load bearing. But anyway, that's another story for another day. So the leg is assembled. We can now bring back our pelvis. Take our spring, make sure it's lined up. Oh, I haven't done these. So there's these to go in as well, which I'll quickly do now. And I usually use M6x6 on the circulars, but as there's more depth, I use M6x10, mainly because I'm running out of stock of the M6x6. And these are like a couple of grams heavier, which is really not a big deal, but there will be a super leggero version of the legs. And that's even a short one there. That's a 6mm, that's a 10. And this will allow the tension, or rather the preloading, on the series elastic actuator to be manually changed. Okay, one more. So for now, in fact, I'm going to have a rotation, or roll rather, with no extra preload. So I'll just back those out completely, make it easy to assemble. So this will interface to the torque output of the motor. You want as much flat as possible towards the back, like so. Press the spring in. Okay. And now we assemble again. So this is a bit longer now. So we want, oh yeah, 60s are good. It's easier if everything just moves freely. Okay. So this bearing goes over the end here. One thing we haven't done actually is we haven't done a little bit of heat in here. So just to make sure that everything fits nicely, what I like to do is do a little bit fitting, just gently put some heat down, particularly into the bottom. You've got some slight angles. Just make sure a bearing all the way down into there. And also just check that there's no swarf or debris or anything else obstructing the bearing from going cleanly all the way down. And you'll see it's concentric. That will help. Okay. So back again. Spring lined up. You just fully press it down. Put our bearings. Engage on the bottom, let's have a look what's going on here. I've missed, is it? There we go. And once everything is lined up, just nip it up gently. At this point, just want to make sure everything is in alignment. And then when you're happy, everything is symmetrical, you can just finish torquing these bolts out. Generally finish by hand, certainly the first time it's going together, to give you a much better feel. How much friction there is in everything. Yeah, that one's tight. Might be because it's pushing through the plastic at the bottom. Didn't feel like it was a cracking kind of tightening, so yes, I suspect that's the issue. So here, because I've pushed the plastic over at the end, I've engaged it, and that's not a bad thing because it'll stop the screws shaking loose, although generally there's quite a lot of tension on these, so I'm not expecting these to shake loose, but you never know. Okay, so now we have hip pitch, hip yaw, hip roll, and a knee joint. You can reinsert the motor. First of all, this pulley goes back on. Just lined it up. The hexagon has not gripped as well as I would like. So I'm going to tighten up all the tolerances on that. And conceivably, might go to a full spline. For now, I don't think it will matter. This first draft is just to test if things fit and if they move. This has now got the clearance to slide up and down. On this one, I left that square, and it was actually exactly the right length, but it meant there was no adjustment. On this one, I've taken it back to a curve. So there is about 5 mils of free play, which for a timing belt with a 5 mil pitch is exactly what you need. So then there is a retaining bolt, a 65, which goes through here. That's too long. What's the length for you? Now that's a 70. That's a 65. And now that can be adjusted. And that'll hold the tension. I will probably come up with a more elaborate mechanism and possibly something which involves sticking something down there. But for now, this will be enough to check that everything works. There's something to be said, still wrong length, for it having a little bit of free play in the event of too much torque, because it means that instead of braking, the belt will release. Did I put the wrong one again? Yes, there you go, 65. Okay. So for now, just put something down there, like a screwdriver, put some tension on the belt. Not very scientific at the moment. Tighten that up. A little bit noisier than the hip. So if the alignment is, yes, the alignment is slightly out. And so the intention, that makes no sense. This is being raised up at this side. Force is there, it should be pulled downwards. Must be something underneath that. That's causing that slight clicking sound. Okay, that can be tuned out. There we go. Can't really see it. I'll do you a better shot from further away. So yes, in fact, there was a very slight error still. There's two little raised up sections here, which I've just pressed down with some heat. And this means the motor can now stay flat when it's in there. So we shall see if that makes a difference to the sound. Belts are very tolerant. It's the advantage of belts, they're very tolerant to error. Disadvantage, of course, so you have to buy them. But compared to trying to print gear teeth across a range of printers particularly, the belts are a much easier option. Still not exactly silent. Still raising up a little there. It's better, but not as good as the hip. Well, I think we can live with that. But that's the thing. I think it's going to become very apparent, is that cheap robots are going to be noisier and expensive ones are going to be quieter, and that's how you're really going to be able to tell immediately, because you can make them look any way you want. But the noise is going to stay expensive. Okay, so I've had one more go at making the knee joint a bit quieter, and that seems to have worked. It was just a slight raise, still a slight raise, but I will continue to tune it out from the CAD model. Now you just have the normal belt noise of it running. Okay, so knee, roll, yaw or abduction, flexion or pitch. That is hip and knee joint of the HOPEJr. Okay, so that is the knee, the roll, the yaw or the abduction, and the flexion. This is the pelvis, one side of it shown. So that is the HOPEJr leg first draft which we'll see what breaks. Powered by 1, 2, 3, 4 Xiaomi side gear motors. Very cheap for the power and the torque, but I've increased the torque with belts, and I suspect I would also increase the torque with the belts on the yaw. Don't think there's quite enough there, but for now at the knee, 1 belt, and at the hip pitch, another belt. Okay, so I think that's everything you need to put the ankle together. I'm just going to start by putting in the grub screws, otherwise known as set screws, into the SEA mechanism. That's just going to be a partial tap to make the threads grip more strongly and to resist coming undone. Wrong one. And these can be used to increase the preload on the spring. And also finely adjust, because there's 3 points of contact on the spring. So, and then bearings need to go into here, that's what I forgot. Where are we? Size is 4 by 7 by 2.5, and 20 of those. And then 2 long bolts, M4 by 80. Or 75, depending on the version. These will need some hot inserts done. Okay. So some inserts are going to go into here. And they will go in hot. Okay. Oh, that one's blocked. So this is what happens if it goes wrong. You get plastic down your mare. That should have been chucked. The way to prevent that is by having plenty of thread sticking out the end. Going to heat that up, stick it in that hole. Just get a slight oxide colour. Don't breathe in the fumes. Make sure everything is lined up. If there's any extra while it's still hot, you can try and push it over. Easy with a straight edge. Pretty good. See shiny metal down there, so you know that hole is not blocked. You just see it down there. That end. Okay. Let that cool down. Get another one, which
Cheers, this soak. Another insert, same procedure. Might left that one too long. So don't waste time. When it's ready to push, do it while it's hot. That's a little out of position now and didn't go in deep enough. That can be remedied with a soldering iron, of course. Just what I'm going to do now. Let it cool down enough that you don't unwind the insert, unwinding the bolt. That one also canted over quite a lot. And then we're just going to push it in with that soldering iron. And this is probably the proper way of doing it. You can actually get special tips that attach just soldering iron to make this job easier. Problem I have found with these deep ones is that it does sometimes block up the hole with plastic. That's quite difficult to deal with. Again, just want to make sure that it is level. Seems okay. I guess one thing you can check is that you can screw in from the other side while it's still slightly malleable. The risk with doing this is that you just hit the insert and knock it out. Yeah, like that. See it start to turn. Yep, this one's got blocks. So yeah, you need to do it through from the far end. See if I can screw through here. I doubt it though. Oh, that's all right. Made it. Just though. Yeah. Not a particularly clean example. Try and do better than that. In fact, I'd go so far as to call that a bit of a cock-up. Nonetheless, that is the effect that you're after. It could maybe be slightly more parallel. They're pretty much in line. And the only real consequence is that when you tighten them up, they're going to squeak a little bit. Not too bad. Clear up any last bits of print support left over. Probably safer to do that with a small screwdriver. And if there's any white residue here, you can also clean that up with a bit of heat. Okay, not too much. I'll just remelt the surface. Usually, just left a little bit there for some reason. Okay, if these are cooled down enough, and these will go in from the other side. Now looking at that, there is a bit raised up, so that needs to be trimmed off with a scalpel or filed flush. Be very careful with scalpels. They are designed to cut flesh and will do so very well if you give them a chance. Where's my file gone?
This particular file is a diamond file, and it's normally used for sharpening whetstones. I used it because it turned out to be very good at the carbon fibre reinforced nylon, but it's just a nice flat plane. The correct way to do this is in fact by turning figure eights. And that will produce the most even grind. Just brush off any excess. That should be pretty flat, because it wants to be a good fit into the hexagon and the pulley. Yeah, there's no movement at all. And in fact, in order for that to pull down, you need more inserts. I'm going to do 3 more in fact. Also, M4. Now, as these ones are not going to be screwed from that side but from this side, these can just be pushed in with a soldering iron, and that makes life easier and faster. And that will need to be cut open again to access, but that at least has gone flat again. Seems to be the quickest way to do that. So heat up the insert a little bit so it starts to go in. Keep it nice and square. Go a little bit beneath the surface. And while it's still hot, push in all of the extra plastic which squirted up when the insert went in, and just push it flat. You can always do a little bit of sanding afterwards, but this will speed things up considerably. And just chop out the middle with a knife, I think will be okay. Just to find out. Last one. Oh, that's better, even. Just chop it off while it's all soft. Huh. Well, that's somewhere in between. Made a bit of a mess in that corner. So if there's any doubt, force it back into the hole while it's all still soft. That will cause it to remold. Okay. Yeah, a little bit of dink there. So these. Just cut open. So I don't like having to push quite hard on this one. Plastic's a bit thicker with next to. So just keep your other digits out of the way of the scalpel, because if it suddenly cuts through and moves rapidly, you can always nick yourself with it. But as long as you can access the threads with a screw, it is enough. Just check that you can screw into each one. Well, that one's out by miles. Huh. Crikey. That needs fixing. That one's okay. Also out by a lot. What's going on there? So, maybe because I'm filming it, but I've managed to put these in very wonky. They should be straight. I have to try and straighten these up now. Soldering iron is not very straight. Might be something to do with that. Right, so it's at this angle. It's going forwards a lot. Yeah, I think it must be that. Soldering iron. Okay, so buy yourself a proper tooling, make life easier. Okay, that's better. And this one. Yes, as they're all out by the same. I suspect that's what I've done. Still not great, is it? Okay, it's better. This one also out. So the accuracy obviously will be affected by this. A bit of a guess, frankly, but most of the torque is taken by the hexagon, so it shouldn't matter too much if the holes don't line up perfectly. In fact, to some extent it will lock it in place. Well, let's see if that still fits. Okay, and then this is locked by M4s. By I think 16. And 4 by 16. Possibly a bit long. I think you could go shorter than that. You need to go into the insert. Anything shorter. 20s. M4 by 12s. Yes, let's go M4 by 12 to secure the ankle pulley. Not many of those left, so I must order some more. As always, the way to start is a little bit of each before clamping down. Oh, I have put one in the wrong place as well. On the plus side, that will give me the chance to try and do one of the heat inserts straight. So this one should also have an insert. Just make sure that it goes in straight, although you can readjust it afterwards with a soldering iron if need be. So when you start off, make sure everything is lined up, and you can see that my soldering iron is a bit wonky. Push it all the way down. Make sure it's just beneath the surface. Still a bit high. Otherwise it will no longer sit flat. There you go, that's better. So very important that the insert is below the surface, otherwise it will no longer be able to screw up tight against the bottom of that. There must be an optimal temperature, but I haven't quite worked it out yet. It's still a bit squishy now to cut. So a surprisingly finicky thing to get just right. And maybe most things are finicky to get just right. Always just heat up the surface a bit. And just run a flat surface over everything. Make sure this last one I just put in is square. It's actually pretty good. And finish with a bit of linishing if necessary, just to knock off any high spots. Brush over the bin. Okay, just check that fits. Still a nice fit. Move one up top. And then one here. Last one. Here, okay. You can torque it down. I think this will be strong enough. I'm not sure for the knee because it's got quite a bit more diameter on the pulley, but for the ankle I'm expecting that to be fine even in PLA. We shall find out. Okay, so that has to come off now. But we can now start the assembly. Okay, to assemble the ankle, I'm going to need M4 cap heads. These are going to hold bearings in. These are going to hold bearings in place, and that will provide a bearing surface against this spring. And when these two mechanisms rotate against each other, how does that look like? They will store energy in the spring. So just tease those bearings into there. These get locked in place. One cap head. Same on the other side. 10 on each side. These are 4mm internal diameter, 7mm external diameter, 2.5mm wide. Despite printing vertically, there should be enough clearance for these to drop in without any trimming. That provides an almost frictionless bearing surface. Okay, the outside of the mechanism, essentially a housing. On some of them there are inserts here, on this one it's just nuts. 4 of them, where's it gone? M60. How can it not be right in front of me? I'll use this one, black and white one. Okay, M4x60, A2 cap head in this case, but you can use anything really. This is one of the stronger parts. Might even drop it to M3, but it will increase the cost. So for this one, I'm leaving it as it is. I've already made sure these all fit together. So, how does this go? Go there. Yes, right, of course. So, what has to happen next? So we have to attach to the front of the motor this housing. No, not the motor. What am I talking about? So in the lower leg, the motor is offset like the knee. So there's a pulley which goes onto there. There is a mechanism. So there's a pulley which goes onto the motor. There's a sliding mechanism. There's a locking mechanism. And then this holds one end of the series elastic actuating mechanism, and on the other passes through the torque from the pulley. Okie dokie, so the way to do this is to get the bearing which fits into there, and that goes on here. I don't feel like I've got that quite right. Is that the same size? It's gone on ever so tight. Something seems slightly wrong here. Yes, it does go like that. Oh no, these have come out tight. It's definitely come out tight. Something strange has happened. I do believe I've had an error. Alright, that should fit. I don't know what's going on there. I've got to check the CAD back in a bit. Well, the CAD is correct, so I'm not sure why that's coming up so remarkably tight. I will try forcing it on and seeing if that does the job. Put a bit of heat to soften it, but it seems weird to me. Maybe there's an edge core somewhere. Try crunching things with these, because that way you can keep things fairly parallel. Well, I think that was just a very tight fit. Didn't seem like that one I did for the knee. And the real question is whether or not this fits. Which way around? I guess. Also very tight. Strange. However, it does fit, so you might have to force it on a bit. But that is how that goes on there. Cool, okay. So, this can now go there. And this will come through like so. This will come through the middle, like so. And on the other end there's another bearing. And the whole thing clamps down thus. And that squeezes that spring in the middle there. I missed one. should go through fairly easy. Look at it sticking out the bottom. That will make it easy to get a nut on. And then once it gets into the hole, it should self-lock. Apparently it has not. Maybe it'll help then. Yeah, actually it's probably because of the plastic here will jam up the thread. It should find a little hole there, which is hexagonal in shape. Still not that one. Oh well, can't win them all. Yeah. When the rest of the foot is assembled, this will be replaced similar to the lower leg, of course, up here. That's surprisingly awkward to do on camera. Blame a lot of stuff on camera, but it is trickier. Certainly slows me down. So you should never really use pliers for doing this. You should always use a socket set, because that way you won't damage things. Okay, so that is the series actuator elastic unit assembled, and of course the last thing, which I should have probably done before, is put a bearing in here, which is, where's it gone? Under my socket set, of course. And this bearing will push apart also the mount for the series elastic, but it will give somewhere for that torque insert to rotate. Okay, so you can barely move it by hand. Because once this is screwed on, it's very free. That's running on that bearing there. Other end is running on that bearing there. And this end inserts into the socket of the lower leg. I'm then going to screw it to these 5 holes with 5 short screws and some inserts, M3 in this case. 5 of them. Same thing as before, just try and keep things straight. And make sure you go below the surface. Be very careful, of course, not to burn yourself. So you can even think about it. You lose the flow state. Okay, so that's 5 inserts. The only remaining question is whether or not this easily fits into that bearing. Based on the others, I'm hopeful. I'm still going to give it a little softening up. Particularly on this end, there's a lot of ends. Oh, lovely. Wonderful.
Okay. That is ankle pitch. How lovely. Okay, so very nearly there now. It hasn't sat perfect up into this corner here. So as always, the procedure is to do a little bit on each, get things started. Very good. Okay, that is the ankle joint in. This can now go back on top of it. Lovely jubbly. And the final thing is to attach the motor to this. Attach the pulley to the motor. And then mount everything up with the belt. Okay. So first this. 20 and 4x20s. 3 of them I think will be more than enough. And 4x20s. Just give this a quick. Actually, no, I don't think this one I'll do. This one I think I screw right through. This is also printed on a higher quality printer, so tolerances are better. Gone as small as I can on this pinion, so in some places the teeth are actually missing. I hope that doesn't turn out to be a very bad thing. And as usual, probably easier to power up while screwing this in, because then the motor won't turn. Okay, so everything's now held in position by the motor torque itself. So these should be quite straightforward to just screw down. Doesn't need to be too tight, but if it's too tight, so we'll just screw the belt. Okay. Show that moving. Oh, very well. Just do it with one hand. Got a lot of acceleration on it. So proof of that works. Kill the power, unplug it, and in order to get this on, you have to undo the 3 screws on the back and then be ready to tighten up with some countersunk M3
by, I think 16 works best. And 3 by 16s. I need to do this by hand because it just gives you more control. Generally a good idea to have made sure your motor works before doing anything like taking it to pieces. Because otherwise you spend a long time trying to work out why you've broken something when it's already broken. So far, I must say, I've been very impressed with the quality of this motor, especially for the price. So those go like that. This just engages over there, and these are a size down. Usually think get lightly started, move on to the next one. So just tighten these all off now. Push it into there. This should be just right on a 500mm belt. Very good. And there is a securing bolt in 4x45. Pushes through there. Clamps on the back. This mechanism is not strong enough, I don't think, so I will be improving it in subsequent versions. But for now, see, already there's a little bit of tension there. Try it. So it really needs a tensioning mechanism. It needs something which pushes against here while you tighten up that, and then possibly locks it in place as well. Because I have found that it's not terribly strong, this clamping, because you're clamping through plastic, of course. Still, for now, I just want to make sure it all fits together. There haven't been any errors on, say, the calculation of belt centres. So I'll just clamp it up as best I can, but it's not particularly effective. If you squeeze here, you can make it move for sure. But it will allow me to test for systems. And now, for example, if I plug back in, I do believe we shall have... Oh, come on! Thank you. A working motor. A working ankle even. Yes, there we go. Pretty fast. So we shall see what the performance is like. Oh, sorry. Shot.
that is the ankle. So pretty fast. Whether or not it'll be enough to jump off the ground, we shall see. Okay, I think that I have everything needed to do the ankle. So all the prints I've been reprinting all morning, but I think everything's correct, so I'm going to try and put it together now. The foot, the ankle, some toes. There are inserts to go into here, which are attached to the bottom of the ankle. Thinking about it, I'll probably find it easier to release this. So that's still not strong enough, so you can just pop that out and release these. Get the ankle out. So that is the ankle, and the foot goes on like that. So that's the lining up required. Quite a lot of preload on the spring, partly because I forgot to add some clearance holes in here, so I've had to wind them all the way in. That's to wind in these adjustment screws all the way. We shall see if that's a good idea once it's all assembled. Having a stiff foot seems like a pretty good idea. Right, so that goes in here, goes like that. So you can check the engagement. I think it might be worth taking that spring out, make life a bit easier while we're setting it up. So just need a couple of these screws. However, as the underside is a clear hole, I think I'll be okay pushing them in with the soldering iron and then just checking the fit once they're in place. I think that will be easier, so we shall try that. So just going to use the soldering iron to push these into the holes, and whilst it is still hot, then check the fit with the disassembled ankle. And like so. Okay. So there you can see how the angle lines up. Good God, like so. Okay, indeed, so you can see it was slightly out. You couldn't see it, in fact. But that now you can be pretty sure it's lined up correctly. Let it cool down a little bit, and then that way, if all four are done, then when you put it together under pressure, which the spring will give some back pressure, it should still be fine. That's the idea. Okay, so that's one. Same again on this side. As soon as it heats up, it'll just start to sink into the plastic. Make sure it's in. Tighten up with that one. And just press it together. Make sure that you can screw that in without too much squeaking. Bit of squeaking is okay. Too much means that it's not aligned properly, and then you'll get problems. Okay. Handy to have the power driver for doing things quickly. Very nice. Okay. Same on this side. Okay. Took a bit longer than I would have liked. Nonetheless, PLA still stays soft for really quite a long time. So in that respect, it's a nice easy one to do. Some of the other plastics, it will stop being malleable much more rapidly. Remains to be seen if PLA is strong enough. My gut feeling is that it won't be. But the PLA Plus is surprisingly good. Well, I tested the design as well, of course. Lost one. Just try and line it up so it's more or less correct from the beginning. Should be fine now. Just zing these in a little bit. And because they are at an angle, that will tend to align everything as well. Maybe a bit more gap than I would like ideally, but should torque up fine. This now is just a clearance, in fact. Okay, so once that cools down, we can disassemble that again and put the ankle back together and attach the rest of the foot. Okay, it's just a few seconds there. should be clearance holes in there, of course. Very awkward to get to, but nonetheless, marginally better than nothing. So I'll add that on the redraft. Okay. So let's get these started so things can't fall to pieces. You'll get a little bit misalignment because of the spring pushing everything out of shape until it's under tension. Oh, ran out of batteries. New battery. Okay. You want a little bit protruding from the end. Because they're not square to each other. Right, so that goes like this. So this goes like this. I shall maybe put some identifying marks on them. But the way it goes is that you've got, this is the drive coming from the motor, and this is the drive which will come from the servo in the heel, and that will tilt the foot over. So this one goes at the back. Get them all started a little. And then you should be fine to torque them up. And still probably a good idea to finish by hand. You'll also get a much better feel if anything's gone too tight or if you've cross-threaded a little. Okay, that seems pretty good. Right, so this is the main inner bearing. Main bearing really, I guess. That should all press down into there. And then there's just some screws to hold it in place. Usual technique, just get them started. Although as this has already been together once, it's probably not too bad. Or rather, probably everything is lined up okay already. If not, you can always get yourself what is affectionately known as a HOPEJr, which is a pointed metal, or in this case potentially plastic stick, which you can use to pull holes into alignment before screwing down other screws. Okay, and then the belt can go back on. So there's some tension, but not quite enough to hold the belt. Up here there is a mechanism which just clamps across a plastic carriage, not strong enough in plastic for high loads. But it's possibly not a bad idea on a test prototype, because that way if something goes wrong, this will just slide rather than it destroying itself. Something to be said for that. Okay, so ankle now has the main pitch joint. The shape of the foot is such, there's not a huge amount of movement on it. that the axis is at an angle, and that means that as it rotates you automatically get a bit of yaw and a bit of pitch at the same time. Total guess, 30 degrees I think it is, maybe not even that. See how it works. Okay, how is this held together now? Right, so there are two servos which are going to drive movement on the foot, and they are both of this kind. I have previously bought the CL version, which is the coreless motor. It's a much older design. The BL, the brushless motor, is significantly better. Remarkably even so. When you run them side by side, it's quite impressive how much better this one is. So this is what I recommend now. There's one which is going to go here, and that will give the kind of combined roll, pitch, yaw, roll, yaw movement. And then there's one which goes in here, the toes come in a box like this. I'm using the 12-volt version. So they come like that, with it in fact already attached. There's a free spinning servo horn at the back, and there's a driven one at the front, 8 points. I'm going to assume they've come centered because I can't be bothered to set up everything to drive them, but you should check the center position of these before you assemble. Should be okay. In fact, yes, it will be okay, because for the heel you can release the belts from underneath. It's not a joined belt. There's a tensioning mechanism built in to the underside of the ankle, and this one, in fact, for the toes, the whole thing can be slid in and out. So it should be easy to fix things if they are indeed not centered. Right, so to attach the heeled servo, you need M3x6, which go on the size of Allen key, which for some reason is not in front of me. So M3x6, which is a 2.5mm driver. Maybe M3x8 will fit as well. I have a feeling that the tapping is not very deep in the middle holes, but I think you can get slightly longer ones to fit in the corner holes. But 4 of them should be enough. In fact, there's a 5th one here. Which I will try a longer one. Let's see if it goes. That is a 10 by the looks of it. Yes, that is 10. No, that won't be long enough. It's a shorter hole. All right, M3x6 it is. M3x6. And that locks the servo in. So these are not series elastic. There's no compliance in the setup at the moment. I might well change that, especially for the toe one. It seems a good idea for the toe to have a lot more shock absorption. This is dead simple, just getting things going. Okay, so there's a pulley. In fact, this one really doesn't matter. This can easily be changed after the event. Some more challenges getting it back on. The spline is tight fitting, so it needs to be lined up well. And when it is lined up well, it should slide down relatively easily. If you've got it at an angle, that won't be the case. And once you get it jammed over, you can damage the spline permanently. So always be careful pushing splines on and off. No, that's good. It's fine. And in fact, you have to put this on afterwards, because in order to screw to these two holes, that can't be slid on with that in place. Might change that, but I like having those extra holes up there. Maybe it's unnecessary. Maybe you can just screw down at the bottom, particularly if I make the heel a bit bigger at the back, so that extra hole can go. So something to consider for the next revision. Also, some bearings need to be pressed into this hole. I have a feeling it might be a little bit awkward looking at it, but we shall have a go. And the obvious thing here is I'll add a centre hole, so you can use a screw to pull those in. And that has come up a bit tight. That might be a bit of a problem actually. I'm going to do a bit of melting on the top here. The hole has gone a bit tight. Come up with a way to make that easier. These bearings are always going to be awkward to push in. So you want it softened, but not actually so soft that you can raise up an edge easily. If you raise up an edge into the hole, then it'll be very hard to slide the bearings any further down. Yes, this needs a better way of doing this. This is going to be a real pain. All right, I might just do one for now, just to... I can see I can even do one, just to get it assembled. Okay, well, with a bit of heat it's all right. Not brilliant. All right, I'll come up with something better for that. And the way that the centre shaft, in fact, goes is it splits with a diagonal cut. So as that gets pulled together, that will make a cylindrical shaft. Just use that to press it in and make sure that it is at least more or less lines up with the front bearings, which you can see that it does. So should be two bearings back there. I'm just going to put one for now in this version. And I'll improve that to make it easier to load the bearings. To get that out. So I haven't done it yet, but there is a hole here which will take an M3 insert. And then that way you can screw something to the end of this in order to pull it out. Just cool it down if you're in a hurry. Now you can screw on. Must admit, didn't expect that. Pull pole bearing out. Okay, well. Yes, so you can see now it's raised up. A slight welt down in that hole. Okay, that needs an improvement. We shall do so. Okay, it will do for now. Right, so next, I guess, yes, all right, so in fact, next is to attach this pulley to the front of the servo. The pulley is 10 mils deep, So you're going to want M3 by 14s, which I presently only have in black oxide. I actually did have some in these 16s. Does seem like it. Yes, got 16 in stainless. Lots of 16 in stainless, but the 14 I think will be better. Yes, definitely 14s. And that should be a snug fit on this centre boss, which will help to centre everything. And you can just use screws to pull it down onto there. This is an M2.5 or 2.5 or T2.5, T2.5 I think the designation is, maybe an MT 2.5. 2.5mm pitch toothed belt, which is this kind of size, as opposed to the larger 5mm we use up here. Less than half the power should be fine. Turns freely, but is minimal clearances. This will now... there is a trap. Oh, it won't go together. It cannot be assembled. Right, so I'm going to have to unscrew the servo, break these off. This has to go in afterwards. It does happen sometimes. Well, there we go. Right, so as it stands, that cannot be assembled. The design will have to be changed. But I think it can be assembled weakly, enough to check that it's physically works. All right, back in a moment. Indeed, so looking at that, what can be done? The servo, in fact, will be held down tight by the belt and it will locate into this square, so the torsional force to take in. So in fact, it will just be one little screw holding the servo in place. And I will indeed have to cut away the top, but then this whole thing will slide in. So what's the best way to get that out? I think... yes. No, that doesn't really help. So the difficulty is going to be getting the spline off. Might come. Generally, you need to be able to pull a spline on opposite sides in order to get it out. But this one has been taken out before. Okay, good. It's loose. So that will just come out like that. This can then come undone. So it might well be worth adding a second screw at the back. So in fact, these will just have to be cut off such that the motor can slide in with the spline assembled. An easy way to do that is just with a pair of cutters. Okie dokie. So I will tidy it up with a bit of heat. You can just, and that way you can just smooth off any sharp corners. Okay, I can now reassemble our servo on the outside, which I guess is probably easier anyway.
Make sure it's square, and it should just slide down easily. Tighten the center screw, which is now going to be more awkward to get to, and if necessary, you can always use a pair of tweezers. That might be awkward given the shape of these things. Pair of tweezers and a screwdriver. Visible. You can hold one and use the other to push into position, and then tighten it down. Okay, we can now put the foot into position on the ankle. There will be another one of these bearings. These are 20 by 27 by 4. Originally I was going to use 2 at each end, but it's too hard to get that one in, so I will change that. Same thing possibly true at this end, thinking about it. Yeah, it's also a bit tight. Bearings want to be tight, but not so tight that you can't get them in. Okay. Generally at the top is where the problems are going to be, because printing circles horizontally or cylindrical holes horizontally is not what 3D printers are best at. I've raised an edge there clearly. Don't think that's quite enough length. So it might in fact be better. Yes, very good. See, there's an edge raised here now. It might be better to have the top of this removable, in fact. Depends how much it compromises with the strength. But it's still effectively an arch, so it should be all right. Okay, I'm just going to smooth this out of the way. Totally different weight will be needed to mount the foot bearings. Okay. Clearly, that's not good, but for now it will do. Get it in a tool. Very annoying. Okay, that's better. Very good. Okay. So we've even got 2 up here. One might be popping out. So we have 2 center shafts. I think everything else will be assembled afterwards. So as many bearings as you can get. They should be all the way down to here. And we'll make that a split, I think. That's definitely the way to go. The fat end goes in first. And wants to... Oh, it's going to be very hard to get out when it comes to it. So I'm going to need holes in both. Try gently tapping it with a persuader. Okay, and that would appear to have engaged a little bit in the back at least. From the CAD, I'll have to check the sizing. So the problem will be getting it to pieces, in fact. I've come to regret this. But that will at least lock Okay, so you got ankle pitch, yaw and roll of some description. I wonder, in fact, if that's gonna... Well, we shall see how that works out. Total guesswork. I would like to have a simulation running first, but didn't get a chance. However, the URDF and the step are out, so if you want to make a step simulation for it, you can. Okay, the heel servo now fits in like so. Sorry, other way up. The heel servo goes in like so. Might increase the range of movement. That is less than I thought, I can't deny it. It's a bit better, but still. Where's it fouling? Yeah, it should come all the way around to here. Odd. Why on earth did that move? Okay, anyway, let's secure this with one screw in the heel. And then the belt will wrap around the top of this servo and is secured by two locking pieces on the underside of the foot. Okay, so these are the two locking pieces, and they will engage on the belt. Here's a piece of cup belt. They will mesh like so, and are then pushed up into these holes here, and then they're secured with a screw. So in fact I need to also put in the inserts, which would probably have been easier done before I assembled it, so you can't really see it. Up in there is a hole, so I would recommend doing those before you assemble the foot. Inserts. Here they are. So two M3s. This is a long M3, which makes life a little bit easier at least. And I'm going to do these now with the gas torch. Heat them up, stick them in. Make sure there's a fair bit of thread sticking out the end. You want to make sure that you can go all the way through this insert. Just until the oxide colour starts to change. Put it in the hole. And by eye, just make sure everything is lined up. To the sides of the hole. Spray in there, cool it down more quickly. Same on the other side. Just push it down. Can't get any light down there with this particular lamp, but that's what you're after. Cool it down. And you can
can tell how much plastic flowed by how easy it is to remove. Okay, so hopefully now this will work. This is completely untested, so that's always fun. This goes this way round. So the belt passes up through this little gap here and will wrap over the pulley, which is attached to the servo, and the other ends will be fastened by these locking keys, which just get pushed into these holes here. That's a particularly annoying thing. Let's just chop that off. Do it the other way, in fact. I guess I must have got it on a bend. Possibly even slightly worse. Try it from here. Okay, like that. Just pinch and push it in. Okay, and that will lock the belt to the underside of that. And we're just going to put an M3 by 25, I think is probably a good length. M3 by 25. It's just a hole in that locking key. Okay, so I'll start them off in that neutral position because I don't know what the length should be. That's going to pass up over there. And then back out here. So there we go. Engage over the top of the servo, and then relative to there, just mark that. I think it's the easiest way to do this. So this will go in like so, and the point at which that wraps around there is here. So when that's tipped over inside like that, it'll be here. That will engage there. So it means we cut it off. Aha, no, make sure it's all pulled tight before you do that. So making sure that everything is pulled very tight. Oh, that's correct, very good. That will engage in that tooth there. So we wish to cut it off here. So, as always, measure twice, cut once. Make sure everything is pulled tight. And really check where that belt crosses that edge. That will engage with that top tooth. You can push it into position, and indeed we're going to cut it off of that one. So, okay. Oh, still cannot be assembled. Rather very hard to assemble. No, that cannot be assembled still. because it needs to be inserted simultaneously and wrapped around. Oh, that's a shame. Okay, I don't know if I think about that.
Happy days.
Okay, so there were a few problems with this, and indeed taking it to pieces is going to be very difficult. I might well cut it open to get those bearings out, because I would rather have 2 at each end, and I've only got 2 spare now. But fortunately, due to the magic of 3D printing overnight, I printed off some new ones, and I have changed the method for securing the ankle pivot now to a split design. This will screw together, it will make it much easier to access things. It may or may not be as strong, still going to be some tight compression fits into these, we'll see how that holds up. So I'm going to remove the supports, put it together, add the toes, and that'll be the first leg done. Okay, so the parts are peeled. In fact, I already filmed this once and the camera just suddenly went black, so I lost the last 5 minutes. Didn't do anything too vital, but I'll just cover it again. The design has now more depth in these holes, which engage the belt, and also the servo can be detached and reattached with a little bit more free play. So those 2 things I'm hoping should make it very easy now to adjust the belt. We shall see if there is enough tension in it. When it's just tensioned up, it might still slip, the teeth are not very deep. So it may require idlers, so we shall see if that's necessary. Swings and roundabouts on idlers versus sliding fixtures and other methods. There's all pros and cons to them, of course, as you might expect. A little bit lost now. Right, yes, I will show you the keys. So the way that the belt is secured is that there is an insert down in there, which you can now access from the top, but I think I will still put it through from this side to keep it clean. And then there is a locking key, which is a nice fit on the belt, and that goes down in such a way that the belt goes over the top of it, and the hole lines up, and then you can screw that down and it will pull the belt in. So that fits nicely on both sides. They are not identical, of course, they are a pair. So this one goes over here, belt comes over the top, and you just tuck it into this hole and make sure it slides down. Which it does. Hopefully that will be strong enough. If it's not, we shall make it stronger. Okay, so what I was doing at that point was simply inserting brass inserts here. This is done with a soldering iron and then clamped up to keep the position correct. So I'll go back over that. So this one, in fact, is slightly out still because I was in the middle of fixing that one when the camera suddenly blinked off and it distracted me. So I will reheat that so it can be reset. And then there's just 2 more to do. The soldering iron is set to 300 degrees centigrade. You can get special tips. Just heat it up until it starts to have a bit of movement again. And then screw that in. And screw on the other side as well. Should just be able to do it by finger, and then that way you know that everything is in the right position. I am not pushing the plastic back down inside this hole. In fact, if anything, it should be removed, because that way the insert, or rather that way the bolt, if necessary, can come all the way through. If you want to be fancy, I guess you could mould it onto the side, or you can just get a knife and carefully trim it off.
really want, you can make it pretty, get rid of all the white cut edges. A bit of heat. That insert is in, position looks fine. Onwards, 2 more to go. So, 300-degree soldering iron, insert goes on, do not burn yourself. Make sure it lines up well with the hole. You've got to prep this, you should have your bolt ready to go, of course. Screw a few turns so it's lined up. Screw these ones. You can feel that one was a little bit resistant to go in, so I've got the angle slightly out there. But that should all sit very neatly. That's the main ankle pitch, and this is the foot kind of combination yaw roll. So previously I tried to use a split centre that needed hammering in, and if you have to start hammering anything, or as it's called, persuading, then you're going to have problems taking it to pieces. And this one, in fact, I can't get to pieces, so I'm going to chisel it open to get the bearings out. This one uses a different system, we shall see if they work. Thinking about it, I should have done a slight diameter reduction to get the bearings on more easily, because they go all the way down to the end, but there's always something. We shall see how we get on with these. And these can be pulled down by an insert in there. So there'll be a pair of inserts, a pair of M4s, which I guess will be removed after they've been pulled in. And the bearings there, which will then sit into these sockets in the foot. This way around. Right, last insert. Just screw those back out. Get everything lined up. Where's the last one gone? Make sure they all screw down whilst pressing the two parts tightly together. Okay. Very good. Really surprisingly tenacious how it sticks to metal once it's hot. It's been more or less pushed out anyway. If you're wondering about these, I have a cat. Just tidy those up. Okay.
and generally we shall see how strong this design is. It's obviously convenient for modularization, but it's not particularly strong join between these two bits, and as a pro that means that if there's a big crash, the robot will split apart in a reasonable way. As a negative, of course, you don't necessarily want the robot coming to pieces when it's doing something that you want it to be doing, so a bit of testing required to see how strong that really is, and I suspect it will vary very strongly between materials as well. So the carbon legs will be quite different, but the general idea is make it in PLA, which is quite a bit weaker, see where it breaks, reinforce that, see where it breaks again, reinforce that, and then make it in carbon, which is about 10 times stronger. No, not 10 times. Actually, for the split strength across the layers, it's getting on for it. So it would be much, much stronger. That is the plan. Okay, now that those inserts are done there are 2 more to go in here. These are just M3. And as it will be much easier to line them up, I'm going to do them with flame from this end, because once this bolt is down, you can make sure that it's bang center. So our technique: heat this until you see the first blush of a red oxide on it. Turn off the heat and stick it down the hole. Oh, too hard. Crumbs. Okay, that was too hot and I pushed too hard. Doesn't want to come out the back. That hole is a bit shorter than I realised. And I might have made it a bit too hot, in fact. That seems okay. You just need to look down into there. I guess you could always put a screwdriver, some kind of a large flat bottom, and that will make sure that the insert is at the same level. And now you can just pull this so that it's dead center coming out the hole. Yeah, don't know, might be easier just to do it from above with a screwdriver, with a soldering iron now, in fact. So let's come up a little bit far, in fact, so I'm going to use a soldering iron to push it back in. Don't want that hitting the belt. Let's see where that's ended up. Yeah, it seems okay. All right, let's see if we can make life easier. Just soldering iron in from above. The hole is at an angle, which is not ideal. So go until it's just below the surface. And we need to make sure we can screw in from the other end. There's a little bit of plastic trap, it's gone a little bit tight. I can get started. Yeah, that might be a touch tricky. I'll freeze it off. Just see if we can push one through from this end. Yeah, we can. So be careful not to get any plastic covering the hole, and you can get them from this end. And the test of that will be with a slightly, well, I guess we can use these for now. Let's just make sure that all fits. That's this one. Which would in fact be this way. It will need to be, I think, a short length is. Not as long as this, clearly. This is a very long M3, which I use for the V1 Dexhand wrists. This, let's have a quick measure. This wants to be an
M3. Actually, could end up being only an M3 by 20, or even less actually. That might need to have a bit of adjustment, because as you tighten it up, of course, it's going to start sticking through that. A bit more to optimise this mechanism than I realised. We shall keep going, but there should be a set of parameters that works out pretty well, and you've got all of the screw engaged in that. Might take a bit of working out. Okay, nonetheless, pretty sure that can be worked out. So keys carefully to one side, all the inserts on that done. Now, apart from these ones, M4 down the middle. And we shall see if we can pull the ankle pivot together. This one shouldn't be particularly fussy, but nonetheless, as soon as it's in, put a little bit of an M4 screwed in, you can just check your orientation. Wants to be pretty reasonable. Seems good. Same on the other side. Okay. Very good. Okay, so in this particular iteration, these are different lengths, which is not ideal. I will probably fix that. The longer one, in fact, is at the front. It's not a bad start. These will take the bearings and then be pushed in, which means bearings have to go on first. And I did not make life easy for myself by adding, or rather removing, say, 1/2 mil off that. It will make negligible difference to the strength and putting on the bearings very easy. So this I'm just going to have to force them on. Might even end up printing a tube to push the bearings, but I'll fix that. I've got 2 ready to go. Yes, we are going to be a little bit, no, not too bad. They're going to go, I think, oh, yeah, I think they'll be all right. Okay, I'll print a tube to help push them down. Whilst we wait for that to print, we can take the bearings out of this one. I have been unable to move this at all. And my suspicion is that when I hammered it in, I ended up welding the two bits of plastic together. But the idea was that you could pull that out. It didn't really work. I'll see if I can do it in the vise. And the answer is yes. Damaged my screw, but nonetheless that did suddenly pop out. I'm hoping I can now grab hold of this with a pair of pliers, and it won't be so hard. Okay, so not a total failure as a design, but certainly awkward, more awkward than it needed to be. But I should be able to get my bearings back now. Right, okay. And this goes on the prototype scrap shelf. And I've got piles of this kind of stuff, by the way. So I've always wanted to give it to members in some, like a sign of joining up. So have a think about how I can do that, and I'll start advertising it. Right, I now have 4 bearings, but no tube yet to push them down. So whilst we wait for the tube to print, we can add the inserts for here and here. This will now house, that's what I do. This will house the servo. So before we do that, let's just draw some clearance holes definitely clear. Seems fine. And the servo can now slide down into here, and this can be reattached. That can now sit there. This takes the belt and the bearings, that sits underneath it. And then there is a bridge, not like Taylor Swift, a structural bridge, which will hold that all together. Okay. So we have 5 inserts to go in. It's good practice, close your boxes when you're not using them. So these bearings should now quite happily squeeze down into these holes. This is already self-locating though, so it shouldn't be too much of an issue. And make sure you don't lose the screw, which goes with that. Okay, so same procedure, use a soldering iron, push it in, and then make sure you've got an M3 ready to go, which will clamp it in place and check the position. Okay, so this one is going to do 25, 25, and something short, like a 10, 25, 25, and a 10. 10, 20, 16, where are my 25s? There they are, right in front of me, of course. And for the other bridge, 25 is a bit long. So 16s. And these are 16s. Okay. Size of these. I'm taking this one. Is it? Okay, pretty good. Right. Which would be best to start with? I don't think it'll make a huge amount of difference. I'll start with that one. Make sure it goes below the surface. Just going to get all my 25s. Very good. Okay, excellent. And you just want to make sure it screws down. Don't actually screw it tight because you're going to pull it back out of the hole. Just want to make sure that it lines up. That's usually pretty good, so that gives me a bit of confidence. Nonetheless, I did them one by one because it's a pain if they go wrong. Push it down below the surface. Lovely. Both engaged nicely. Last one. See, that's pretty good actually. Excellent. Okay, so the heel will screw on nicely, we'll clamp those bearings, we'll take the servo, give a lot more flexibility, and it's only a minor increase in complexity of the design. So that is acceptable too. The toe servos need to make sure they fit. They are going to go in here. This is the right foot, so the big toe is going to be on this side, like so. And in fact, this will assemble outside and slot in as a unit. Very simple for now. It's just flexion. There's no series elastic. There's no nothing. As simple as it can be. Just checking principles of operation. Okay, well, that's good. That's in. Okay, we can check the bridge fits, and this doesn't have a self-aligning function, so I'm going to put a bearing here. I'm going to put 2 bearings here. That way they shouldn't fall over. I think it can split. These holes could arguably go a bit higher, but then we have to add some bosses here. We shall see. It's a problem which goes away with the carbon fibre, so I'm not that bothered. And the holes are also in slightly the wrong position on this version, but not to worry. Okay, so couple of surface. Well, fortunately that does fit because I spent a lot of time faffing about with that. This technique seems to work very well with the pre-formed holes. The inserts go in pretty straight. It's really just on this piece, possibly because we started at an angle, there's more problems. If the insert goes in on a flat surface, it seems to be okay. So that's good. And of course there's a little bit of clearance, not a lot in fact, but a little bit of clearance. Screws are not exactly 3mm and M3 is about 2.85 or so. Okay, so that is how that will fit together. Here are our bearings, to be done, so I can do that as well. So we are still waiting for the print finish. Alright, let's go and see how it's doing. Not long to go. Done it quite dense, maybe too dense. Okay, as that is still printing, we shall do the toe assembly. Toe comes in 3 parts: big toe, small toe, middle. Slightly different versions in this one, but you get the idea. You're going to screw it together. Driven side has the spline. It attaches to the large servo horn. There must be another one somewhere. Okay, tube is done. Okay, our tube is printed. And that will allow us to push bearings nice and easily all the way down. Keeps everything square, because the problem with pushing hard is that if things lock up, or rather, if things twist, they will lock up. So you need to keep everything
square, and this will help with that, which is why it's a tight fitting. I've only given, in fact, I gave it a millimetre clearance, and that's come up reasonably tight, because this one, of course, was printed sideways and this one was printed upright, so you will get different tolerances. Probably less of an issue on a more modern machine, but certainly on my old printer, something to watch out for. So you need to get them started square. Right, so now we shall see how we go into this. So long one at the front, short one at the back. Now it might just push in and be okay, or it might be necessary to use the screw in the middle. And the same thing, wants to stay square as it goes in. Okay, so don't need that for this particular set of parts. Well, let's see if this one's the same. Strength-wise, probably better to do it this way round. Don't know, interesting. I'll put flats on because otherwise you get issues. We're only very small flats, but you can get, it just doesn't print very well, so you won't get a very good cylinder. Well, I guess I'll do them opposite, because that one I've done that way, and this one I'll do this way. Somehow it feels like the fatigue life will be better if you've got the flat there, whereas this is going to put more stress directly up into, I don't know, maybe there's nothing in it at all. Okay, see if that fits. I do like 3D printing. Oh, that is just lovely. First time straight in. What a phenomenal technology to have access to. Really has democratized precision engineering. Which is, if you know anything about the history of computers, is in fact what the problem that Babbage had. It was not... how sure does that go? How many of these have I got? Do I need it? Actually, don't need it on this one. This one just needs the pulley. Sorry, I got distracted thinking about Charles Babbage there, who invented the mechanical computer, but in his lifetime never got to see one made because he could not find enough workshops that shared the same unit of measurement. The precision was not the problem. It was the fact that different workshops had their own tools and there were no standards, which is a bit like robots. One of the key things that has to happen is the development of standards. Something along the lines of the way that you can build a PC. You can order all these components from all these different vendors, and this by magic put them together and they will produce a working computer. That has to happen for robots too. Sure it will at some point. Right. So, onwards. To put the foot together, I'm going to take that out and reassemble the ankle joint, in fact. So, you have the spring and the carrier for the series elastic actuator mechanism. Spring in the series elastic actuator casing, bearing there, and another bearing inside here to make that all relatively smooth. A little bit of a catch somewhere. That clamps onto there. One side is slightly flatter than the other. And just push those together like so. they get stuck, you can always wind them in with a screwdriver, or in this case a power drill. Down like that. The other end has, oh no, let's do that again. To assemble the series elastic actuator mechanism, this bearing needs to be put in position there. That can be dropped like so. That's easy. That's where they are. Go like so. This clamp normally has one side slightly better than the other. Push the bolts in. It gets stuck. You can always use a power drill. Just get a little bit sticking out the bottom, and do the same on the other side. Okay, and just check which way around that goes. This is the back of the foot, and now you also have these holes which line up with the adjustment set screws for the spring tension. Should be able to carefully, in fact I wouldn't do that by machine at first, because if something goes wrong and you cross your threads, it's going to be a pain to fix that. So just gently by hand, because that way you can get a feel for it. Make sure that the inserts and the screws are lined up. Okay, and then you can finish torquing it up with this. But again, by hand is probably the way to finish. Just nip that up. Okay, so that is the series elastic pulley. As you can see, by hand, you can really barely move that spring. Under the load of a motor, I'm expecting it to compress by 5, 6, 7 mils. Hopefully not enough to ever get over the edge of that spring on those rollers. Maybe one day it will. I'd be impressed if it does, but who knows. Okay, so I've not done this before, so I'll have a little think. That is going to drop into there. That's going to be held by the bridges and the heel. So the heel, where's the heel? Heel is here. The heel holds this servo, in fact, like so. This is one of the 85M series. Just drops in the bottom and is secured by M3x6, I think it is. You can go M3x8 in the corners, in fact, but in the middle, the thread in the hole is very shallow. This is an 8. It's a 10 actually. That's 10. This is 8 for the corners, and that will make it a little stronger. Very low on those. And then there is one more in the back, which is probably unnecessary. I suspect that the rest of the attachment, that can be a 6 again in fact, I suspect that the rest of the attachment is stronger than the plastic to which this is bolted to, so by definition it's pointless. but I've done it, so I'll fit it. Okay, so that secures the servo. The spool has already got the capstan, what's it called? Pulley? Yeah, tooth pulley. It's already got the pulley on it. I think these are just M3. That is the centre screw for the servo. Let's see if an M3 fits. Seems better to use an M3. Okay, I'll try one for now. I'll probably use a 6 in the end. Okay, very good. So a lot of the servos use a strange, or rather an unusual size. They use a M2.3, and they're very hard to find. But an M3 is standard, and I've got bags of them lying around, and somewhere I've got some 6mm long ones. Okay, so you can use obviously the centre screw which comes with the servo, or you can replace them with an M3 cap head, which I would suggest is definitely better. I've already got the M3s in here, so this should now just drop into place. So that screws there. Screws there. And then there's just a small one here as well. Torque those up, that's pretty good. Guess might as well screw the front at the same time. Didn't feel like the other one really was closing up yet. I think actually on the holes are slightly wrong on this one, but I've already corrected those. On the CAD server release version will be okay. It goes a little tight. Let's see how that beds in. I might add a little bit more clearance. A little bit of contact. So these might have to be changed for countersunks or something else. Yes. It just hits. That did not show up on the CAD. Okay, so a little bit of finessing to do on that. For now, I'm just going to replace these with some shorter screws. Okay. The advantage is that it is easy to remove. In fact, this whole assembly needs to move slightly backwards because it also just fouls with the outside of the ankle. But I was too far committed in the design to make that many changes in this draft. So the ankle will be a little restricted. It won't have as much movement as will be possible in the, I guess, the release version. Although I was planning to just release this as it stands. Although I don't think anyone's going to be able to get hold of the motors very easily. So, you know, but as a gesture, I can release the STL files. If you're still listening and you would like that, do let me know in the comments. It's helpful to know what people need. Okay, so these may have some shorter types. Yes, I do. So these are 14. Won't have short type 14s, I don't think. Sixteens, 10s, 12s, 14s. Ta-da! Now you may say that I overbuy, and you would almost certainly have a point. But sometimes it's just exactly what's needed. And then it feels like a very good idea to have overbought all of this stuff. Huh. Okay. Life's strange like that. What's up with you? Didn't like that. It's just full of stuff. Let's try another one, shall we? Right, we're going to say that was just because it was bunged up with plastic. Thread looks okay, so we shall try it. No, thread is definitely damaged. So my advice, if you do have a damaged, or you do damage the screw, chuck it away. So otherwise you'll end up using it again when you don't mean to. Very nice. So I shall need an extra, and I've got 10. Happy days. Might have to do a bit of a tidy up soon, but just pushing to get this finished basically. Because then we can connect it all up and get it moving. Okay, so let's see what that's like. And I'm just going to lose all of them. Well, we can live with that. So that is the lock to lock of the ankle. That is the pitch. So the belt to attach, and then just the toes, and we can reconnect it to the leg. To drive the ankle rotation, there's a belt, which I'm fairly sure is going to be a little bit too short, unfortunately, but we shall have a go. We tuck that down inside there. You can see that it emerges down here. And then that is held in place by a pair of keys. And they have holes which you can then pull against. So this one ideally will have that much engagement. I already cut this and then realised that I could not in fact assemble it as it was. I'm not sure that there will be enough length now. We shall see. And this one. Ideally would go there. Oh yeah, looks small. Oh. That's an awkward thing to do. Can't be done any other way, don't think so. I think we might go away with it. Okay. So, the question then is there enough travel? Yes, there is. So, screwing those two keys down ought start with a 20, tension the belt across the pulley, which is now attached. No, 25. Start with 25 at least. Might end up with 125 and 120. Let's see, 25 here. So drop in to the hole, into the hole. Start tightening those up. So not tight enough yet, but a good start. And you can see the screw emerging. Okay. That's a fair amount of tension on that. We shall see if this mechanism is strong enough. It's very experimental, of course. Looks like I need to, yes, definitely. So I need to fill it off this corner, because I would say that belt is presently getting caught on that corner, which might be a good thing or it might not. Well, that's not too bad for now. We can look at improving that mechanism, but the point is just to give it balancing stability, which that does, and also a doubling of torque. So this is an 85 kilogram centimetre, which means we're now getting 170 kilogram centimetres, which means that across here, which is 8 centimetres, you've got, well, if it was 10 it would be 17. So you've got, you know, getting on for 20 kilos, which is what you need on the out, on the very edge of each. So it should be strong enough when it's standing on the ground with the full weight of the robot on one leg to lift itself up onto that edge. In theory, we shall see when it's all put together, and we shall see what happens when and if it's carrying a payload. But that is the foot and the roll mechanism assembled for the first time, aside from the toes, which we shall do now. Okay, to do the toes we need one more 85. This has no increase in torque, but then the moment arm is very short. So the basic idea is that all of the torques, when multiplied by the moment arms over which they can affect, will come up at around about 20 kilograms of applied force. Possibly higher in the hips, actually, thinking about it. But that is, everything needs to be matched. There's no point having super strong toes if your legs are too weak. It's not going to have the effect you want. So things need to be balanced as far as can be done within the confines of the rest of the design constraints. These servos have a driven side and a free side. The big toe, which is this one, is going to screw to the driven side. The little toe is going to free wheel, and this block between is going to hold them together. So this just needs some insert pressed in. This is all going to be N3. There's 4 of them, so I shall do 4. Just make sure it's below the surface, is all that really matters. There's a thinner end which will engage in the hole, possibly even before the insert has started to heat up, and that will help with location and accuracy. And then I don't bother to twist it. Now there are also these holes on the bottom of the foot, but if anything gets added to those, I'll just do the inserts later, and that's so you can screw on grippy bits of rubber and stuff. Right, so that's the inserts done. And I haven't set the 0 position on this, which is probably a mistake, but that needs, I would say, 6s actually. And I know I've got lots of those, so where'd I put them? Let's just do a couple for now in case I have to move this around. So the driven side is the side with the name on. And you can tell because you can backdrive the gearbox. So I wouldn't do too much. They're not amazingly fond of being backdriven. And then this, just line it up, otherwise it'll be a pain. Similar thing. And this one I would leave loose and do it up after the middle has gone in. 4, 8, 2, 3. Doesn't really matter on this one. Okay. And then this has quite short ones as well. They should probably be longer actually, but for now, yeah, that doesn't seem great. We'll just stick with the 6s because it makes life easy. But that's not contributing a lot of strength from the rest of the plastic structure, so it's a slightly odd decision from me there. I suspect it's because this started out being done a different way. 6s are not long enough. Okay, so there's 4 mils of plastic there. That's not so bad, I guess. Right, so we need at least 10s, maybe 12s. Tens will do. Why are you not going through there? Really? What's going on? What happened there. Okay, so once they're all started, you can finish them off and be sure that things are going to stay aligned. And the little toe support now just be fine to be screwed in as well. Spare hole there, took it out because it wasn't enough material here, and 1 is enough. Okay, do it up nice and tight, finish these ones off. You are screwing to plastic, do not overdo it. And that is the toe assembled. I don't know what you call it, simple assembly, but nonetheless, total guess. Right, this now slides into the foot. And there is scope for adding extra bearings, which I'm probably not going to bother to do for now, because the purpose of the first draft is just to check that it can be physically assembled. Right, those are going to need probably 10s as well, actually. And the kind of thing that comes in later drafts is that you go through and you unify as many of the fasteners as you can, just to reduce the part count. A bit long. But it's not lined up perfectly, so something is wrong with those holes. Yes, they are slightly out. What's going on here? Definitely slightly out. Not a lot. Seems like it's tight. Okay. No? There we go. Okay, so out by just a very small amount, but enough to make it awkward to screw that servo in. Oh, they're both high. Maybe it's just some swarf or something back here. Okay, so they've gone, but they're slightly off. Easy fix. Okay, there we are. So that's as much as you can go up. Well, might chisel a bit off there just to make that a bit more. That seems not quite enough. Yes, could do a bit more than that. Or maybe that ends up just being a... Anyway, easy to fix. We shall tune this, cut some off, I think. That is the foot. We can now reassemble it, add it to the leg. Okay, here is the rest of the leg. I'm going to space a bit here. There's the lower leg. Is there. So this, which is going to be complicated by wiring, but right now this is just mechanically attached like that. And then there are 5 of these. Which have all become a little scattered around. One of the first things I will do, one of the first things I will teach my intelligent robot to do is tidy up. So that when you turn your back, it just puts all the tools away back to where they should be. That seems like that would be very useful. I wonder if it'll end up being incredibly annoying. But nonetheless, it's the kind of experiment I'm expecting to be able to do really quite soon. There we are. And that attaches the foot. We need a timing belt, 10 mils, 10 mil wide, 500 teeth, 5 mil pitch. Okay, and this mechanism also needs to be improved. But for now, it's simply a single cross bolt in a slot. The advantage of that is that if anything does go wrong, and let's face it, it probably will, the motor will slip and it will limit how much torque can be transferred through the system. Actually making things powerful is a different set of problems. For now, we will settle for everything moving. Toes, roll your combination, pitch at the ankle, knee, thigh rotation, your direct drive at the moment, although I'm thinking it will probably end up, so I'm certain it will end up having a belt. Oh, come all the way back round. so. There we go. That's pitch, and misses for pelvis, or half the pelvis, so a bit's missing there. So that is finally one right leg. So here it is, finally fully mechanically assembled. Hope Jr. right leg. We have got toes, ankle pitch, combined yaw and roll, knee, thigh rotation, thigh yaw or abduction, pitch or flexion, and this is a half pelvis.